I think we are missing Manolis Ploumidis, which is one of our speakers. We might as well get started, I think, with Christian's talk. And first of all, I would like to welcome the attendees. Thank you for taking some time to attend this event and perhaps interact with us. We are grateful to have a good set of panelists, all of them with significant experience in this field. And again, they took some time out of their schedules to be here with us. So we're very much obliged for that. So there will be a sequence of talks, and then there will be a panel. And during this time, you can use the Q&A feature of Zoom to post your questions. Petar and myself will be monitoring that so that we can relay your questions and comments to the speakers. Okay, so without further delay, allow me to introduce our first speaker for today, Christian Engelmann. Christian, welcome. Thank you for taking the time to be with us. So Christian is a senior scientist and group lead for intelligent systems and facilities at Oak Ridge National Laboratory. And he has been quite active in this field that is the topic of our workshop. Among other distinctions, he is a senior member of IEEE and ACM, and he has quite a lot of activity, quite a lot of hands-on activity, if I may add. So today's talk by Christian is about smart and resilient extreme scale systems, and he has been considering models of faults, prediction, extrapolation to future generation systems, quite hard challenges. And I look forward to hearing what he has to say. Christian, welcome again. Please take the floor.
All right, I am assuming you can hear me.
Yes, and we see your screen in presenters mode, so we see. Yes, exactly. Thank you.
All right, so I would like to thank everyone. Thank you for inviting me to give this talk. Also, thanks for attending. My name is Christian Engelmann. I'm a senior scientist and a group leader at Oak Ridge National Laboratory. And the group I'm leading is called the Intelligent Systems and Facilities Group, which is a relatively new group. And we're actually still looking for people. So if you're a senior person in the field of intelligent systems, autonomous systems, and so on, you may actually want to contact me because we have open positions. Oak Ridge National Laboratory is a relatively large US Department of Energy research lab. We have about 5,000 employees. We have oftentimes the largest supercomputer in the world. Right now, we don't. Right now, the largest supercomputer in the world is in Japan. But we are currently building the first exascale machine that will become online likely later this year, early next year. And with these kinds of big machines, we do have resilience problems that we need to solve. And I will go over a little bit of the research we have been doing over the last 10 years, although I have been at the lab for now 20 years and have been doing this type of research for 20 years. So why are we talking about resilience? What's the motivation here? Resilience in these types of extreme scale supercomputers is actually an optimization problem between the key design parameters. Performance, resilience, and power consumption. You can make a system very, very fast, but it's not going to be very reliable and it's going to consume a lot of energy. You can make a system very reliable, but it will not be very fast and it will consume a lot of power. And you can make a system consume very, very low power, but it won't be very fast and it may not necessarily be very reliable either. So the challenge here is to build a reliable system within a given cost budget that achieves the expected performance. And you have to trade off. You have to find the right trade-off between these three parameters. This requires a fully understanding of the resilience problem and offering efficient resilience mitigation technologies. First, we have to understand what's the fault model of such systems. What faults, errors, and failures do we actually see and why? What's the impact of faults on applications? How do the faults, errors, and failures actually propagate to then application errors or application failures? And how can certain mitigation techniques help and at what cost? So what we basically started to look at is, okay, we have had all these different supercomputers over Oak Ridge National Laboratory has basically a history of running supercomputers for 30 years now. And we looked at the last several supercomputers, in this case, 5, and started to analyze, okay, what has been going on in the systems in terms of reliability, what types of errors and failures are we seeing and why, and what's the distribution, and what's the mean time between failures, and so on. And this actually work here analyzed 1.2 billion node hours of logs from 5 different systems. And first, we of course had to develop the tools to analyze this, mostly actually scripts that went over the data. Then we also had to actually get the data. For some of these systems were actively running when we analyzed them, so we could actually access the servers where all the data was stored. But some of these systems were already dead. They didn't exist anymore. They were deconstructed. So Oak Ridge National Laboratory, we actually maintain a lot of the data on tape archive. And we had to retrieve the data from tape archive and then to analyze them. And what we did was basically looked at spatial correlations, we looked at temporal correlations, we looked at a variety of different features of the failure data and tried to basically come up with some meaningful analysis and meaningful lessons learned from the data we are seeing.
Christian, sorry to interrupt you. Can you switch to full size presentation mode? We see also your notes as speaker, but the graphs are a bit small.
Oh, okay. I didn't.
Apologies for not checking earlier. Thank you. Apologies for the.
I didn't realize that you have the wrong. Hold on. It's just shared the wrong screen because I'm actually literally looking at the presentation. Let's see. Can you see it now? Hold on. Can you see the big screen now?
We are waiting for the screen to form. Yes, let's give it a click.
It's sharing on my side.
I only see the notice that you have started sharing. Perhaps if you have more than one monitor, the application is a bit confused.
Yeah. I will stop sharing again and do something else. Let's see if this works.
So this is a good example of what you just mentioned. You know, you cannot make it fast, resilient, and low power, right? So it is.
So what are you seeing now? Do you see anything? Otherwise, I literally have to.
Same as before, Christian. So we might as well go back to the previous regime.
No. The problem is that I'm basically stop sharing, start sharing, and Zoom just doesn't care. Okay. Otherwise, I have to leave Zoom and come back. All right, I will literally have to quickly leave Zoom actually to get back to this. Hold on.
Well, in the process, we are giving some time to other people to come to join the session. Apologies for this technical, let's say, inconvenience. We have been spending disproportionate amounts of time in this type of things, and we still don't feel quite comfortable with them. Anyway, let's see. Christian, we have a good visual from your side now with a slide on characterizing supercomputer faults, etc. Thanks for this.
Yeah, I literally had to leave the Zoom session and come back. Okay, now I can go back to this. Okay, so yeah, let's go back to this slide first. So basically, when you look at this graph, what you see is the scaled mean time between failures of all these different systems. And what we mean by scaled is we scaled them based on node count. to make them a little bit more comparable, because we know that the mean time between failures scales roughly with the number of compute nodes. And what you can see there is some of these systems actually jump around quite a bit in the mean time between failures, and some of them are relatively stable. And it's quite difficult to understand what's going on here. And something that's interesting here is that two different systems actually almost jump by an order of magnitude in terms of the mean time between failures. Going up is great, right? So the system becomes more reliable. But it also means that we have basically told application programmers to checkpoint at a checkpoint interval that's, for example, below 5 hours in one case, because we expect the mean time between failures to be less than about 5 hours. But in the end, it was something like 40 hours. So, and they checkpointed way too often, right? So this is sort of one of the examples where we had basically lessons learned. And when we go into the next slide, we look at the different types of failures we're seeing. And I don't have a lot of time to basically go in detail over these, but I can show a little bit. So we have certain types of errors that always happen with whatever generation of systems we have. All these systems, by the way, are Cray systems. It's the MCE error, right? So this is a machine check exception error, which is typically some type of double bit error that occurs, right? So this happens, of course, with every generation of systems. It's a known error, and it just happens at different frequencies, and it typically has to do with memory DIMMs or with memory that's going bad over time, initially throwing a lot of single bit errors and then start throwing double bit errors, and then it needs to be replaced. But we do have other errors and failures that we see that we only see with one generation. And in this case, the issue is that we saw this failure and then reported it back to Cray. Cray identified the root cause of the failure and then said, okay, with the next generation of system, you won't have that anymore because we actually fixed that, right? So we do have this sort of a split problem here, that some errors and failures are the same. Some errors and failures are never the same. They're typically only discovered once and then fixed in the next generation, right? And that's one lesson we learned here, is that with every new generation of supercomputer we are also seeing a new generation of errors and failures. Some of the old ones are still existing and we know how to deal with them, but we always see something new that is just crazy and we need to figure out how to deal with it, right? And sometimes the impact is not as bad, but sometimes, as I will show you in a later slide, it's actually really, really bad. So when we look at the temporal and spatial distribution, the top line of the graphs shows the failure arrival times for 3 different systems. And the red line is actually the mean time between failures, and the blue distribution is actually where those bins are of the various different arrival times. And you can see that the mean time between failure is nowhere near where all the failures are. It's just the mean, right? Because the distribution is not just a normal distribution where we basically have sort of a Gaussian distribution or something like that, right? So we need to keep that in mind when we talk about mean time between failure. Mean time between failure is literally just a measure for the mean, and it doesn't necessarily mean that everything happens around the mean or before the mean or after the mean, or right after the mean or right before the mean. For example, with all these systems, we basically experienced short periods of high instability and longer periods of stability. And we need to account for that when it comes to, for example, checkpointing strategies or any other type of resilience strategies that we are employing. In terms of the spatial distribution, which is sort of the second row of graphs, those graphs don't tell you much unless you really drill into what these graphs are saying. But there is some spatial distribution, spatial correlation going on, depending on heat temperature distribution, as well as also scheduling. And I will show that in a later graph with one specific failure mode. The last series of graphs are QQ plots, where we basically try to fit the failure derivable times into failure probability density functions. And Weibull fits the best here, which is sort of known that Weibull, which has a number of factors that you can deal with, you can make Weibull fit the best. So let's go into details about what types of errors and failures are we actually seeing. And I will show you the most problematic one we have seen so far in the 20 years I have been at Oak Ridge. So Titan was a supercomputer at Oak Ridge National Laboratory that was ran, I think, from 2012, basically late 2012 into 2019. Quite a long period of time to run for a supercomputer. And we had GPU failures. And early on, we had basically here this the number one phase, which basically is sort of the early failure phase that you always see, where you need to fix something. You discover a problem that needs to get fixed. And then we had another phase, the number two phase, where there was also something discovered that we had to fix. And both of these cases, we sort of expected rework cycles where one of the major root causes was that soldering points were not made correctly. So when the GPU was heating up, parts of the GPU connections were disconnecting from the board. And that meant basically that the GPU suddenly had some disconnected connections from the PCI bus. And that meant that the GPU performance was now lower because it had less PCI bandwidth. At some point, it also went off the PCI bus, where down at the lower graph, you can see the OTB error. That's the off the bus error when the GPU basically is disconnected from the bus. But I will talk about mostly of the failures that in the phase 3 of this, where we basically have this upper graph that basically shows how many GPUs we have sort of swapped out of the system and when, and the lower graph basically shows the failures of the quarterly failures of the GPUs and what type of failures. One category is the off the bus error, failure, which basically means the GPU literally disappears. In this case, in the third phase, it was literally the problem that the GPU was dead, it was done. And then we had this double bit error phase where the GPU would constantly throw a ridiculous number of double bit errors. And the root cause for that is the same as the double bit error of the bus error root cause, which I will explain in the next slide. But what you can see here is that somewhere in 2015, we suddenly saw a drastic increase in GPU failures. And we basically had this batch of old GPUs where the last GPUs were basically replaced in 2014. And they were just failing at a drastic rate. And we had to basically decide what to do about it. Do we actually buy a new system or do we replace the GPUs? And we decided to replace the GPUs, and we ended up replacing 11,000 out of the 18,800 GPUs. That's a lot of GPUs, and it's a lot of money that was spent on just replacing the GPUs because they were failing. So to basically talk a little bit about what's going on here, this on the left side, you see the sort of a cutout from the GPU board. The GPU is on a separate board, not on the main board. And you can see that there was a resistor that was not an anti-sulfur resistor. And we had sulfur deposits on that resistor. And we had what's called silver sulfide corrosion, which changed the value of a resistor. And that meant that the GPU, there was some reference voltage that was changed, and that meant that the GPU was basically burned over the years because it was just running a little bit too hot, and then over time it would just wear out very, very fast. And on the right side, you can see sort of some nice picture about the deposits that we actually discovered. I have to tell you that finding out this root cause took several months. The boards were basically sent to NVIDIA, to Cray. We at Oak Ridge themselves also looked at them, tried to identify, okay, what's going on here, and trying to measure what actually broke and try to find out which component broke, and then try to figure out why. And once we figure out where the sulfur, that we had a sulfur contamination issue, we also try to figure out where it came from. I think we never did. We even had chemical sensors in the machine room that couldn't pick up anything. But that was basically the root cause of the problem. And that meant that we basically had to not only swap out the dead GPUs, but also, of course, the entire boards, because you can't just take the GPUs off of these boards anyway. So when we then look at the sort of weekly GPU failures, what we can see is that we had these GPU failures ramping up rather drastically over a short period of time. And then at some point it peaked, and then it went down again because we started replacing things, right? So this is sort of the remediation. And the remediation happened until December 2017. And after that, the system was stable. This graph doesn't show the last several months of 2019 because the numbers went up slightly again. The system became more unstable again because the old GPUs will start dominating the system. And what you can also see here is that initially the mean time between or the weekly GPU failures were actually relatively low, right? The initial phase was really low, but then the peak phase was really extremely high. To the worst case scenario was we had a GPU MTBF of 2 hours. And that's really, really bad, right? So when you have a GPU failure in the entire system every 2 hours, and you have to take a node out every 2 hours, this means you can't schedule large-scale jobs, and you have to figure out what you do about it. So we did swap the GPUs, but we also changed our scheduling to the point where the new GPUs were getting more of the jobs, large-scale jobs, and the old GPUs were getting a lot of the small-scale, short-running jobs, for example. And the roughly stable period at the end is still 21.7 GPU failures a week, which is still 3 GPU failures a day, which is quite a lot, actually. So the analysis we did afterwards was kind of interesting because we first had to actually understand the data and sort of define what GPU life means and start processing the data. And you can see a lot of things here on this graph. So this is basically GPU lifetime ordered by serial numbers. So this is each line of these is each individual GPU. And you can see some GPUs actually have a blue dot at the end, which basically means they have an off the bus error and are basically end of life, they're done. They have a red point at the end, which basically means they had a double bit error and we took them out. Or they basically just disappeared and reappeared again, where basically we moved the GPU from one computer to another, which we did as well as part of the mitigation. Or you had just GPU lifetimes that just ended without any color, where basically some proactive replacement happened, where we basically said, this GPU is part of the old batch. It has a lot of single bit errors already. It's pretty much close to getting done. Let's replace it. So this is already some interesting view. And this view is actually based on the compute nodes. Remember that we actually move GPUs around and we replace GPUs. So we want to have in the compute nodes the small amount of holes as possible, because we need to make sure that we keep the system operating at full capacity, right? So you can see that we have off-the-bus replacements, we have double bit error replacements, but then we also have proactive replacements, and then some blade neighbor of replacements, these kinds of things, where we literally just swap GPUs around, right? But then we have other interesting effects where Up here in this area, we have a proactive replacement, and then the node comes online again and actually has a double bit error. So we actually put an old GPU in it, and the old GPU immediately throws us a double bit error. And we took it out, we put another old GPU in it, and it throws us another double bit error later on again. And then we took the node offline for quite a while and then put another GPU in it. So this is also some interesting point in the data. And when we analyze the data, of course, we did the traditional reliability analysis of MTBF, and you can see that the number of failures are, again, are pretty high, and the MTBF is getting pretty low. And you can see sort of different binnings of MTBF per years, where we see certain spikes and so on. And this is all interesting analysis, but how does this translate to any sort of other system where, you know, the failure may be different, right? So what does that tell us? This tells us a lot of the system we had, but not much of any sort of future systems and any sort of lessons learned. Instead, what we looked at is sort of the survival probability of individual, in this case, nodes, and where the node is located on the compute board and in the cage. And we can see that the top line here is the new nodes, the new GPUs. So we just ignore them. The bottom line is the old ones. And you can see that certain nodes, for example, the green one, node 1, is actually the most unreliable one, and the red one as well, right? And why is that? Well, the red one is node 0 and the green one is node 1, and 0 and 1 are actually on the top part of the board, and airflow goes up. So airflow basically first passes over node 2 and 3, and then goes over node 1 and 0, and node 1 and 0 are therefore the hottest ones. So we can see that. And we also can see that cage 2 basically failures are the highest ones, right? The survival probability here is basically the lowest one at the end, right? So that means that cage 2, which is the top cage, is also the hottest cage. In this case, we literally can show that this failure mode basically also had the factor of contributing factor of heat, right? So that heat was actually primary driver of this failure mode, right? And that's an interesting lesson to learn here, that we need to, when we design future systems, that we focus on heat distribution better, right? So more about that as well is that this looks at sort of hazard. So this is an analysis. You have to look at the supercomputing paper from last year to fully understand what we did here. What we did is basically we looked at hazard analysis. We did not assume any sort of different specific failure distribution in this case, but instead looked at statistical analysis used in the medical field, where when you have basically a certain virus floating around and people dying of this virus, you also do not know what the distribution probability distribution of that is, but you can assert some hazard ratio based on different factors that contribute to that, right? So, and that's what we did here. And what we did was actually looked at the different hazard ratios and looked at sort of how the hazard ratios fit in the heat distribution within the system. And we could see that the other servers that were in the same computer room heated up a certain part of the computer room. And that meant that that part of the computer room was more prone to these GPU failures. But we also could see the fill-in scheduling, that the more certain computers were used, the more they were also failing, right? So this is also an interesting sort of lesson learned here. So yeah, so this is all what I want to say about this failure mode. We can certainly in the Q&A session have more discussions about that. I would highly encourage you to look at the more details in last year's supercomputing paper, where we did a lot of this analysis. Now, a lot of analysis we did over the last decades basically was based on scripts basically, or using R for statistical analysis, or Python scripts. And this can be quite problematic because it takes a long time. You need to format the data. You need to develop the scripts. The scripts are typically specific for that computer. And when you get a new computer, nothing really works well again. So what we started doing is developing this infrastructure where we basically look this from a perspective of having sort of a more of a professional analysis framework. So we started developing this log scan framework, which is an experimental framework. This is not a production framework, where we took the data from Titan, for example, published it into Kafka, and then streamed it from Kafka into a Cassandra database where the data was already tagged before it actually even landed in the Cassandra database, which made analysis later way more easier. We had a Spark Spark engines to run a certain analysis. One Spark engine was, for example, a synchronous Spark engine where you just issue a Python call and the analysis would run and the Python call would come back. Another one was an asynchronous one where you issue the Python call comes immediately back because the analysis could take 8 hours. And then after those 8 hours, you basically issue another Python call and check for the results. We had a graphical user interface that was a web-based interface to basically browse all the data and sort of the analysis results. But we also had a Jupyter Notebook front end to analyze the data to basically make sense of this. And we did various different analyses with that. For example, we looked at the impact of system reliability events on the applications on Titan. What we could see is there is some slowdown in terms of, for example, these machine check exceptions or Lustre errors and out of memory errors, failures. Here in this case, it's basically you have an application that failed somewhere in the system, and that application failure actually slows down existing other applications that don't fail. So this is sort of an interesting side effect that we have been seeing in these systems. And this needs to be studied more, and we need to have better analysis systems. This is actually one of the conclusions of this talk, actually. We came up with what's called system information entropy. Studying entropy is sort of a typical method for statisticians to look at data. It's basically just classic Shannon entropy theory, where you apply principal component analysis and then look at, okay, how much of each of these components changes when something happens in the system, right? And we did sort of principal component analysis based on event type, based on node location. So there's a sort of a spatial information there, but also just based on event counts, right? And we have gotten some interesting results here where we can see that sort of drastic changes in the system information entropy reflect some changes in the system reliability. But there's definitely more work needed in this area as well. This is just the math behind it. It's not that complicated, actually, if you look at it more clearly. So now I've talked a lot about analysis. What about, okay, how do we actually deal with these types of failures? What do we do with all this? And over the last 20 years, we have developed a lot of different solutions. Later today, we hear talks about checkpointing and redundancy. There are naturally fault-tolerant applications, or there are resilient applications. There are applications that are self-stabilizing. There's forward error correction. There's something like active standby or end modular redundancy. We have rollback, we have roll forward. We even have rejuvenation, where we just proactively do something. We have restructuring, where an application may fail and we just continue with less compute nodes and try to recompute the failed data, right? So there's lots of different things we do, and we of course need to also have monitoring and maybe some failure prediction as well. So all of these things we have, and what I came up with was basically this concept of resilience design patterns, where we use the design pattern concept to architect systems and deploy these design patterns in a way that we use them as sort of templates for solutions that we then later develop in reality. And what this allows us to do is to basically figure out, okay, where are holes in the protection, right? So where are these protection gaps? Where's overprotection? Which level of the software layer or hardware layer can actually do which protection better? We can do all these different analysis, design space analysis, basically. And we have come up with the resilience design pattern specification, with a taxonomy of design patterns, with a survey of existing solutions, with a pattern anatomy, classification, a catalog, and a language. We also developed a solution for that using a GMR solver with portable multi-resilience that is resilient against process failures and data corruption using two completely different methods. And those methods can be traded off. Right, this goes back to the initial talk motivation where I was talking about trade-off of the different design factors, right? Performance, resilience, and power consumption. And yeah, so we came up with all these 31 identified resilience design patterns that I basically have in this graph down there. I won't go over this right now because I don't have the time. But the current design pattern specification that's out there is a little bit outdated. I'm working on the final version of it, which was supposed to be released by the end of 2020. But I'm still working on the fine-tuning some of this. We have, for example, mathematical models for the reliability, performance, and power consumption of these design patterns. And I want to make sure that we have those in the pattern specification as well. What can you do with this? For example, in this case here, you can sort of compose a design patterns and then do design space exploration, right? So you can figure out what is the optimal solution, right? So for example, in this case here, you may have a heartbeat monitor and BLCR, which is a system level checkpoint restart layer, and then sort of this checkpoint restart solution that protects basically processes. But then on the other side, you may have a matrix A that has a checksum correction algorithm implemented, and you tap into the system software and basically use the ECC detection that basically tells you that there's a double bit error in hardware and notifies the operating system about that. And then you basically tell the operating system, hey, if you see this ECC double bit error happening in this matrix, don't kill me. Don't kill me and fall over to the Berkeley lab checkpoint restart, to the system level checkpoint restart solution, but instead let me do the checksum correction because I know how to do this, right? So this is, for example, one example of how to do this. There are lots of other examples, and we are currently working on practical implementations of this, right? So one example, for example, of a practical implementation is to have a runtime environment that actually implements different pattern instances and provides then a resilient environments for HPC applications. This, what we did here is basically, again, this together with this previous prototype we had of the resilient GMR solver, where we basically protect against soft errors and MPI process failures. So it's not that necessarily that revolutionary in that sense, but it still shows that this can be done if we basically put money into this and if we come up with a coherent strategy, especially if we can integrate this into programming models, where we basically can provide resilient strategies inside programming model runtime environments, right? Or inside operating systems. But this needs to be a coherent effort that actually goes inside the programming models, inside the operating systems, right? And this is just a paper that was just published at the PRDC conference last month. So what are sort of the future research and development needs? We need to certainly design HPC hardware and software ecosystem to be able to deal with high error and failure rates, because we don't buy systems that will be highly unreliable, but we will see them because there's something unexpected that will happen that will basically put us in the back seat. And then we have to basically say, okay, what the hell are we going to do about those high failure rates? So we need to design them from the start to be able to deal with high failure rates. And that requires a lot of things, including understanding what's going on, having the ability to do a cost-benefit trade-off, and having sort of different resilience mitigation mechanisms as a toolbox. And resilience should be a part of the design and not as an afterthought, because resilience is a cross-cutting effort, right? So remember, after 25 years, or now almost 26 years, MPI is still not fault-tolerant. Well, PVM, its predecessor, was fault-tolerant 28 years ago in 1993, right? So this is sort of an issue that we have been dealing in the MPI community, that we have been trying to basically get fault tolerance into MPI for the last 10 years. And it won't be there for the next 5 years either. So we need to basically come up with reasonable solutions, and that need to be part of this toolbox. I also mentioned already that we need to sort of have a portable system and center monitoring and analysis solutions that collect the right metrics, do proper identification of faults, mostly online while the system is running, and then have fast and accurate root cause analysis, which can be online and offline, and using advanced statistical techniques, machine learning, AI, etc. Right? So, and there's some ongoing work at the facilities right now to do this, but it's disconnected from recent research, and there's also a funding problem here. We also, of course, need to have low overhead software mitigation techniques beyond global checkpoint restart inside the operating and runtime system and runtime environment. Inside the programming model runtime environment, we need to have resilience for workflows, for example. This is also work that's ongoing, but it's mostly underfunded, and the community adoption is very, very low. There are two other slides here I want to show where we're going in the future now with smart systems and facilities. Think of it where we have a monitoring system deployed that automatically finds out that problems exist and can autonomously react to that using resource management by basically employing some of the resilience mitigation techniques completely autonomously, right? So this is autonomous resource management that considers the system and facility state and involves the trade-offs, right? And then we do automatic adaptation of systems and facilities in real time to emerging reliability issues, for example, using AI. This is called machine-in-the-loop operational intelligence, where an OODA loop is used to improve productivity and lower costs. And this is the future where I'm going right now with my research group. And resilience in federated and distributed and complex computing systems, an emerging topic as well, as we are connecting instruments and laboratories using edge and center computing resources for science and science feedback on experiments. This is a real-time problem, actually. So this is a real-time resilience problem. And this is also an urgent computing problem. So this is something that's a little bit unusual, and will have the resilience community has to deal with that as well. And then understanding the resilience problem in non-form Neumann architectures like neuromorphic computing is something of interest as well. And I already talked a little bit about resilience by design, that we need to do design space exploration and programming for resilience, and resilient algorithms, definitely probabilistic and approximate computing as well. And then last but not least is the integrity of data and computation as a whole, meaning end-to-end resilience. How do we guarantee end-to-end resilience? And with that, I would like to finish, and I'm open to any sort of questions.
Thank you, Christian, for a most, let's say, exciting talk. There is a Q&A section where people can post their questions, but I don't see anything pending so far. Allow me to ask a question about the aspect of having architectural patterns. I understand that you have put quite a lot of effort there. How do you see this going forward? You mentioned MPI. I understand the level of frustration about MPI, but in the end, MPI is, let's say, a dominant software base for quite a lot of work in our field of HPC. Do you see a way for these ideas to influence MPI developments, for example? It's kind of a long-winded question, but I would be most happy to hear your view.
Yeah, so MPI, right, we have already done some prototypes, right? There's a fault-tolerant MPI prototype. There's a redundant MPI prototype. There are other prototypes that did resilience in MPI. And the question is really, how do we standardize this, right? And there has been a long discussion about that. And I think the convergence is toward what the sessions proposal now is inside MPI, which is sort of the idea that you can create an MPI session where and make that session then fault tolerant, right? So, but it's still a long discussion. But MPI is not the only programming model, right? It's maybe the only programming model for a lot of people, but it's not the only programming model. There are task-based programming models where there is already resilience built in. I have looked at resilience in OpenMP as well. Unfortunately, in OpenMP community themselves, they have not really taken a look at this, pretty much largely ignored it. And this will come back later to bite them when it comes to even just basic error handling, which is the same problem basically that MPI faces now, right? So yeah, so there's that. The architectural patterns are basically all these different ideas, all the different solutions, what you can do. And you need to basically implement them in a reasonable way inside a programming model. That does not necessarily mean it's implemented inside MPI. It can be on top of MPI, where MPI just basically provides basic fault tolerance capabilities, and then you have a higher level programming model that allows you to do resilience, right? So I mean, realize we have programming frameworks like Trilinos, for example, right? Trilinos uses MPI, but there's a lot of other things going on inside Trilinos, right? So I think there's a lot of opportunity here. And I do see some of the other questions, so I can start answering them.
Yes, I would say it's a good tie-in to check these questions. So one of the colleagues is asking about the MPI versus PVM statement that you had.
Yeah.
If you can provide some perspective on that and follow up on that question. Do you see that it's likely we go for resilient systems in future exascale?
Yeah, so we have to, right? So on the quickly answering the questions, MPI versus PVM, right? So for those who are a little bit younger, do not remember that PVM was basically sort of one of the predecessors of MPI. There were multiple different message passing solutions during that period of time. And the idea was to come up with a message passing standard. And one of the discussion points was, should there be a runtime environment that maintains state? And this was in the mid-90s where this was discussed. At that point in time, MPI was considered to be a message passing library that was a communication library that was not supposed to maintain much of state. But for fault tolerance, you need to maintain state. You need to maintain who is basically, and you need to maintain state across the system, not only within each application rank, right? Within application rank, you still need to maintain state, like who else is part of your communicator, these kinds of things. But when something fails, then you basically need to change the communicator, right? And you need to basically have sort of a reconfiguration mechanism for that. And at that point in time, it was decided that that type of state management was not supposed to be part of MPI. That is how I understand how this happened, right? So and in the future, exascale systems themselves will still rely mostly on checkpoint restart as the only resilient solution. There will be some, as I mentioned already, some task-based programming models that will have already built in resilience. But if you run API, you still basically run like you run before. You have to do checkpoint restart. But checkpoint restart will be mostly run relatively fast because of the node local non-volatile memory that you have, stable memory that you have that's on the node. That's where you basically checkpoint locally, and then the checkpoint can slowly drain out of the power file system. So you do have some multi-level checkpointing that will help you with that. But then in the long term, I see that we need to deal with resilience as systems are getting larger and larger, and we run into this a problem of process technology getting smaller and smaller, and having more and more problems with the hardware. It's just inevitable.
Thank you, Christian. A further question. This came in the chat privately. Do you think that CPU and GPU vendors are willing to provide failure in time estimates for their chips, or at least a useful range? That might be information that is a bit restricted, but perhaps you can comment a bit more as a big, let's say, installation for this type of vendors. Do you get this type of information?
Yeah. So the funny part is I'm still showing the resilience design pattern slide. The person that was initially doing this work is actually working at NVIDIA inside the resilience effort, actually doing exactly that. So basically, NVIDIA, for example, also process vendors, they do processor vendors, they do have the internal reliability estimates, right? They do architectural vulnerability analysis. They do all kinds of internal analysis. NVIDIA and other vendors had also contracts with the US Department of Energy to improve this, actually. So I reviewed a lot of their work, but unfortunately it's all on a non-disclosure agreement, so I cannot talk about it. But these numbers exist. And when a vendor like Cray, for example, builds a system, they get to see those numbers. And when we, as a lab, sort of acquire a system, when we do these, basically call for the proposals, and we get the proposals in from the different vendors about what machines they're proposing, we do see those numbers. Right, so we do see sort of these estimates of mean time between failures for individual components, and how all this then propagates up to the estimates of the compute nodes and so on. But the problem is not that. The problem is emerging threats, right? So it's really the problem of the unexpected failure rates. So something quickly to mention on the current Summit system, what we had was, we had one application that was running very close to the margin of power gating, where the GPU is basically running too hot and needs to scale down. But it doesn't scale down because it runs right at this margin. And the problem was our power supplies were not designed for that correctly. So we had power supply failures of the compute nodes. Now the power supplies are redundant, so we had fail over and fail back, but over time they would fail. So we had to replace 9,000 power supplies just because of that design problem, right? So these are the kinds of issues that we are experiencing in real life, where we have to sort of deal with that.
Right. So Christian, a follow-up question by this gentleman. Are these data that you get to have some feeling about, are they workload specific? Are they generic for a wide range of workloads? Can you comment on this part as well? I mean, it's an aspect of the operations view of a supercomputing center, right?
Yes. So within our analysis, we certainly saw that it's workload specific, right? So I always tell people, a system that doesn't get used doesn't fail, right? So that's the most reliable system. Just don't use it, right? So depending on how you use different components, they will fail, right? So if you don't use the GPU heavily, then the GPUs won't fail as much, right? If you don't use a lot of memory, then you won't see a lot of memory errors, right? So usage always defines the failures you're seeing.
So thank you for this. So to check other questions from the QA, there's a question if you can elaborate on the Plexus work on the runtime system. I guess this is still an active research effort at your group?
Yeah, so unfortunately, we are sort of running out of funding on this. So this is the biggest problem with this type of work, is that we have a lot of interesting solutions, but at some point, these are prototypes. These are proof of concept prototypes that then need to sort of feed into other work, feed into programming models, right? Feed into the work of the MPI programming model, feed into the work of the OpenMP programming model, right? So so one of the question was what I mean by resilient strategies, right? So the idea is basically, for example, let's take OpenMP, right? So OpenMP, you can do target offload. You can offload computation from the CPU to the GPU. Why don't we have a micro checkpointing at that point, at that layer, right? So where if the GPU code that I offloaded fails, why don't I have that checkpointing layer where I can just restart the kernel and rerun it again on the same GPU or on a different GPU, right? This would be easy to do within the OpenMP runtime environment, and it would be fully transparent actually to the programmer. The programmer would just need to enable that feature, right? Another interesting feature is also just redundancy, right? So I could say, okay, within OpenMP, I do the GPU offload, but I do it redundantly. I actually, because I want to make sure that this result is correct, right? These are two features, checkpoint restart and redundancy, that could be built into the OpenMP runtime environment as sort of different resilience strategies that are only used on demand when they're actually really required.
Thank you, Christian, for this. So going on to the questions, there is a question there that the context for that is numerical weather prediction. For example, seems that we have the possibility to do, let's say, mainstream style of checkpoint and restart, at least for the coming generation of machines. So the question with this context is that new facilities probably will be bringing new types of failures. And do you see any evidence of mean time between failures to go very critically low for operational purposes? So are you worried that our mean time between failures will actually become worse? And how this would affect the applicability of techniques, or likewise, which techniques do you see as coming forward as very important?
Yeah,
more important.
So that's a twofold question. So one part is we certainly are not going to buy systems that don't work, right? Why should we buy a system that fails every 5 minutes, right? So the systems will they will come with some type of reliability, right? Whatever reliability that is. And they will come with some type of mechanisms like checkpoint restart with node local storage, where we can quickly checkpoint and quickly restart, for example, right? To deal with this issue. So I don't see, I certainly see that vendors themselves, so some chip manufacturers, as well as also the integrators like Cray and or HPE now and IBM and so on, they have to take a closer look at what type of strategies they need to deploy when they deploy these systems, right? And whether checkpoint reset itself is something they can continue to focus on or not. As I mentioned, one of the solutions is, for example, to do checkpoint reset at different levels, right? We don't have to do global checkpoint restart. We can do local checkpoint restart. We can do node level checkpoint restart. We can do GPU level checkpoint restart, and so on. A lot of people don't even know that the IBM Power Processor itself, the Power 8 and the Power 9 processors, they already have inside the processor themselves a tiny, tiny checkpoint restart core. If the IBM Power Processor identifies a corruption of processor state, the processor actually does an internal restart that looks to the user on the outside like a timing error, or not a timing error, just a penalty, like a cache penalty. So these types of techniques already exist, right? So there's definitely a lot of things we need to learn here, but there is sort of this problem that a lot of manufacturers will face over the next decade, basically, where just process technology will become a problem, where we face reliability problems, and we will deploy different types of accelerators that we haven't really used in the past, like maybe different types of chips, neuromorphic computing chips, or specific AI's accelerators that we have not had a lot of experience with, where we need to have some other solutions.
Thank you, Christian, for this. So there is, I remind people that there is a panel at the end of our session, so you have the extra motivation to stay with us. And I think there is a lot of follow-up questions, perhaps to these comments that Christian made, even after this material that he presented. Also, one other item that I would like to bring to your attention, that if you've seen our webpage for the event, we mentioned the European RAS initiative, and Christian was kind enough to provide some feedback and serve really as an advisor for us. So we're grateful for that, and you see that he's done quite a lot of work in the field. He's quite enthusiastic, even after so much time in the field. So I think this is something that is of worth and note. Thank you again, Christian. Let's move to our second speaker for the day, Professor Yves Robert. Yves, can you, do you have good audio from us? Can you project? Great. Okay. Yves is a professor at the Computer Science Laboratory at ENS Lyon, and also a visiting scientist at the University of Tennessee at Knoxville. Among other distinctions, he is a fellow of the IEEE, and he has a long and very comprehensive set of contributions in the area of scheduling techniques and resilience algorithms for large-scale systems. So he's going to give us a short talk about his work on replication and efficiency concerns about that. Yves, thank you for joining the session.
Okay, sorry, I had a connection problem. Do you see my slides okay?
Not Yves. We have good audio from you. We saw starting to share your title slide, but now we just see the speaker's view. Yeah.
Okay. Sorry. So where is it? I use I'm sorry, let me start again. Sorry for there's always a problem.
No worry.
I don't see my preview window. Let me try again.
So sorry, while we're waiting for the new speaker to set up the equipment, something that Christian did not mention, probably because he's too kind and he didn't want to do self-promotion, is that another place to discuss resilience in Europe is actually a workshop organized at the Europark conference that is organized by his team. And I was there this year, and it was very nice environment to discuss work in this area. So if you have any work that could fit there, please send it. And that's all.
Okay, I'm sorry, for some reason the preview file disappeared. How can I do this? So what do you see now? Nothing?
Not something. Yves, do you have two screens? Perhaps this is usually a problem.
No, I have a single screen.
Okay.
Let me.
It did start to show
Yeah,
your title,
yeah.
but
Then
then
it was interrupted. So.
Yeah, and you have full rights as far as I can see from Zoom, full sharing rights.
Okay, maybe I can open the file directly. I'm sorry about that.
So you can either share the full screen or start from the share screen menu and pick up the application, only the application.
That's what I did, but the application has disappeared, so I can't do it again.
Okay.
Sorry for that. Oh, okay, it's back. Here should be better.
Great. Yes. Yes, very well.
Let me go full screen.
If you can go full screen, yeah.
Is it okay?
Yes, we see the full screen now.
Excellent. So sorry for the delay. Let me start by thanking the organizer for inviting me to give this short talk. This will be about replication. And the last questions were a very good introduction. Do we believe in environments where failures are so frequent that we need replication? Or don't we? We'll discuss that maybe a little bit at the end of the talk and during the panel. But for sure, at the very least, we need to build models. So in this talk, I will try to explain you why replication for HPC could have been improved in the previous approaches and our solution to do it. Okay, so scale is the enemy. This is well known. If you take a node whose MTBF is 1 century, you're fine. But if you take 100 of them, the MTBF is reduced to only 1 year. Why is that? It is easy to see on this little picture. There are 3 processors. They are each experiencing 20 thoughts during some time frame. Altogether, the 3 of them experience 3 times as many thoughts. So the MTBF is divided by the number of resources. Intuitively, this is very easy. So going on, if I assemble 1,000 nodes, my MTBF is a little more than 1 month. If I go to 100,000 nodes, it's only 8 hours. And clearly, 8 hours is not enough for some applications to run. So we will need to checkpoint at some point. When do we need to checkpoint? As Christian mentioned, there have been many studies. So there's this trade-off to find. If you checkpoint too frequently, you lose a lot of time checkpointing if you don't experience failures. On the contrary, if you checkpoint too infrequently, then you're good for the checkpoint overhead, but each time a failure strikes, you have to re-execute a lot of work. So the optimal solution is well known. It's called the Young-Daly formula. And it states that you should checkpoint periodically. And the period length, which I call capital T, is something like square root of 2C, where C is the checkpoint time, times the MTBF of the platform. So this mu n, that's the MTBF with n processors. So it's the individual MTBF mu divided by the number of processors n. And there have been many mathematical derivations to compute this optimal period and the corresponding overhead, which is defined by my little formula, expected time divided by base time, and -1 to take the overhead. So this is the well-known and well understood. Let's move to replication. So replication, people don't like it in HPC because by definition, you lose, quote, lose half your platform doing redundant work. So your efficiency will be, by definition, limited to 50%. However, there have been a couple of studies, an old one by the Sandia guys in 2011 at SC, and a more recent one by Pittsburgh guys in SC 2018, showing that under some scenarios, replication is still your solution. Let's see. So what's the model? Instead of using n nodes independently, we arrange them into pairs. And each process is replicated on a pair. Why is it interesting from a resilience point of view? Well, clearly, if a replica, one node in the pair is struck by a failure, the computation can still go on. The application will only fail when both replicas of the same pair have been hit. You see here on this little diagram, pair 1 has 2 processors, one has been hit, but it's okay, the execution can continue with the first replica. Same on pair 2 and pair 4, and pair 3 has not been hit yet. in any of its replicas. So many failures will strike statistically before both replicas in the same pair are hit by a failure, leading to an application crash. Let's take some numbers to see why replication can be interesting. If you have big nodes or failure-prone nodes with MTBF of 5 years, how long do you need before you have a 90% chance of fatal failure? If you don't use replication with 200,000 processors, it's 12 minutes. But with replication, it's 85 hours. So in failure-prone environment, replication can save you. Okay, what do we do to checkpoint while replicating the nodes? How often? Obviously, you want to have a longer checkpointing period because by definition, you have a resilience with your pairs. So you will, as I said, you will restart the application only when it fails, meaning that both replicas of a given pair have been hit. So what is the optimal period? The first thing to compute is how many failures will need to strike in expectation before the application will fail. And then if you do this, you can say, well, the mean time between failures is mu. If I need 200 failures before my application to fail, I will say that the application mean time to interruption is 200 times mu. So I will replace the MTBF by the MTTI, the time to interruption of the application. How can I compute this expected number of failures that are needed to bring the application down? Well, you can come up with a nice formula which shows that, in fact, many failures will be needed before the application fails. Recall that B here is the number of processor pairs, so it's 100,000 if I had 200,000 nodes in the beginning. So many failures will strike before your application crashes. Let me skip the math and the explanation with Maple. Just to recap, if I have no replication, I checkpoint with a period dictated by the Young-Daly formula, 2 mu c, where mu is the MTBF of the platform. If I use replication, I checkpoint with a period that's similar, replacing the MTBF mu by the MTTI m, where m is, again, the number of failures needed to bring down the application times the MTBF. Okay, but this is not, contrarily to the Young-Daly formula, this is just an approximation. This is an analogy, if I should say. Are we safe with it? Maybe not. Let's look at it. Here is an example of the classical approach. Pair 1 is struck in the beginning. Pair 2 is struck a little bit later. Pair 3 is not struck at all. And pair 4 is struck the first processor. But then when the fifth failure strikes, the first guy of the first pair is struck and the application crashes. But you see on this example that while in the beginning we had 5 good pairs, the situation has degraded as failures went on striking the platforms. One pair was reduced to a singleton, and then another pair was reduced to a singleton, and so forth. So it's kind of risky not to do anything about these pairs which have become single nodes because of the failures. So instead of doing this classical approach, we advocate the following approach. Each time we checkpoint, we regenerate the nodes that have been struck. This way, from one period to another, all pairs will be fully healthy. And the only cause for the application to fail down is when in the same period, two processors of the same pair would crash. This is shown at the very end of my example here. This seems much safer, and also the probability of failing is reduced clearly. So the period will be possibly much longer, which is very good for the I/O pressure on the platform. So let's analyze this strategy very quickly. So in a nutshell, each time I checkpoint, instead of simply checkpointing, I rejuvenate all the processors that may have failed during the period. How much does it cost me? Well, let's keep the detail. In addition to doing a checkpoint, I do a recovery. So in the worst case, it's twice the cost of checkpointing. If I use in-memory or buddy checkpointing, it's maybe of the same order of magnitude as a pure checkpoint. And the overhead may be negligible compared to a pure checkpoint. Anyway, we are mathematicians, so we use a formula. We will vary the cost of checkpointing and recovery between C and 2C and see whether it has an impact or not on the conclusions. Doing some maths à la Young-Daly, you compute the new optimal checkpointing period, and indeed, it is much longer. I'm not sure I have time to do the digression, but I just wanted to show you here that with one pair, which is not very HPC, the optimal strategy is not periodic. So when you have one pair, both processors start healthy, but when one is hit by a failure, you should reduce the checkpoint period if you don't rejuvenate it. That's very strange. Anyway, let me show you some overheads. First of all, let me state what I'm comparing with. So the classical strategy is no restart, and the optimal period is the analogy with Young-Daly. It's no restart MTTI. And in our strategy with restart, opt is the optimal period computed by our formula. The solid lines are simulations, and the dashed lines are from the theoretical model. I plot the overhead in the y-axis, so the lower the better. The red is our new strategy. The green is the old approach. And the blue is some add-on. It's something in between. It's the new approach with the old period. Just to state that the new approach is more efficient than the old one, regardless of the period you would use. If I use simulations from traces instead of randomly generated, you see on the left the trace from LANL 18, which is uncorrelated, and the adequation with the model is good, while on the right, the trace with LANL 2 is highly correlated, and there's a discrepancy with the model because the failure rates are not distributed according to an exponential distribution of independent failures. Okay, let me skip this one too, and show this one, which is very important. It shows that the period length is really one order of magnitude higher with a new approach. So you achieve a lower overhead while checkpointing significantly less frequently, which again, I think is the most important from the platform point of view, because the I/O bottleneck is a well-known problem, and all applications aim at checkpointing simultaneously, which slows down the global efficiency. It's important to speak about time to solution, not only overhead, because that will tell us whether replication is useful or not. So we take an application that obeys the Amdahl speedup. If you don't use replication, the parallel fraction is divided by the number of nodes. But if you use replication, of course, the parallel fraction is divided by half the number of nodes because the other half is used for replication. So you lose a lot here. Also, you lose some overhead factor alpha. It comes from the Sandia paper because when you do replication, there is some overhead. For instance, instead of having one message from one node to another, you have 4 because you have 1 per replica to 1 per replica on the other side. So some overhead, some formulas. Also, we compare with partial replication because it has been advocated as well. And as expected, you see that if the MTBF is low enough and if the number of processors is high enough and if the checkpoint time is high enough, then replication is much better. And partial replication should never be used. I will conclude here because I will skip this. Maybe just a word. A natural question is, well, you've decided to rejuvenate processors after each failure, after each checkpoint, sorry. Can you do something else, like rejuvenate when half the processors has been struck, or 1/4 the processors has been struck, or every second checkpoint? So there are several alternate strategies to explore. In conclusion, the model is realistic and we achieve smaller overheads with less I/O pressures. So there is no reason not to use our new scheme as opposed to the old one. And of course, I don't know the future. So I contrarily to what Christian has said, I will never predict how efficient or how robust will be the nodes in the next platform generation. For sure, we assemble more and more nodes. Or if we don't, we assemble bigger and bigger nodes with lots of GPUs. So the number of components itself is increasing if you call component a core or a GPU. So there's for sure something that needs to be done about resilience. And my strong belief is that you need models so that you can, and publicly available models, so that you can play with all parameters and see what's good for your application running on your platform. Okay, thank you very much.
Thank you, Yves, for a very interesting talk. I think it's clear that there is quite a lot of background work to provide this summary, so we appreciate this effort. So there is a question in the QA control that I'm going to read to you. What do you think of using an impaired number of replications? I assume this means a node number of replicas. For example, 3, so that the majority gate can be used to choose the same result. So I guess the question is if this work can be extended beyond pairs and perhaps add this majority or voting control in the model.
Okay, so yeah. Yes, but maybe for a different target. Here we deal with crashes or phase stop errors. So there is no need to vote. The processor crashes and we know exactly immediately which one is dead. However, if we target silent errors, then the processors don't crash, but they lead to different results. And indeed, if you have triplication, you can take a majority vote. So yes, there have been several studies, including from our group, this was joint work with Argonne at that point, with Frank Capello. We assessed the optimal number of replicas to cope with silent errors on the HPC platforms using replication and voting. We did not try yet the restart strategy because I mean, we could combine both types of errors, and that it would be interesting to see what's the outcome.
Okay, that's quite an interesting comment, Yves, about the restart strategy. So I'll ask one more question. There is this possibility of having correlated errors. I understand the current model assumes, and you actually provided plots that show evaluations using two different traces, one with, let's say, independent errors and one is correlated errors. Can you expand a bit on that? How does it affect your approach to modeling this environment?
Okay,
Do you
so,
overestimate? Are we, let's say, totally in a random state? Can you expand a bit?
so let me answer your question with two arguments, one from the theory side and one from the practical side. From the theory side, these uncorrelated events are dramatic because they prevent any analysis. If the errors are not independent, all the theory goes down. And there's, to the best of my knowledge, some papers have been published to try and argue about the distributions of error, but because you lose the memoryless property, you cannot say anything on the full platform. So to give you an example, if you assume that your processors are struck by failures following a Weibull distribution, that's very fine with one node, but with two nodes, I mean, the minimum of two Weibulls is not a Weibull unless unless you rejuvenate all the platform after each failure. So on the theory side, it's very bad. On the practical side, as I think Christian mentioned, when failures strike in a burst, well, better let the platform, breathe and resume computing after the burst is finished. So I think that it's true that outside the burst, the instantaneous failure rate is constant. And an exponential distribution is a very good approximation. So, okay, file systems, they have burst. And errors are chained, and you cannot do anything until the problem is solved. But outside these small windows, I don't think it has any impact on the calculations in practice.
Yeah, thanks for this. I had in mind the storage aspect, that perhaps if we have correlated errors, then really it's not exactly hopeless, but impractical. But I understand your argument that if I focus on the computation per se, then I can probably handle bursts. Some sort of recovery action will take place, and then we are back into the area operating state, let's say, that this theory applies, etc.
Exactly.
Okay, we can perhaps pursue this further during the panel. I don't see any other question. Petar, do you have a question from your side for the speaker?
No, sorry. I just have a comment that we are out of time. Sorry,
yeah,
I'm taking taking my eye on the watch. I mean, a lot of interesting data, Yves. I mean, we were doing a lot of this statistical analysis, a lot of models, and fully agree with a lot of things that you said. And or actually, I have a question, right? Sorry. I mean, we are out of time, but I will ask. If you mentioned in order to understand this, we need publicly available models. What about publicly available data?
Oh, that's a very, very good question, and I've been asking everybody to provide me with traces. those you get access to, they are very old. I mean, the LANL platforms, they have a few thousand processors, and each time it's a nightmare. I mean, I did some work analyzing traces using blue waters, but only one of our co-authors was authorized to access the traces and analyze it, and she wouldn't be allowed to discuss the data fully. I mean, these data are proprietary by the vendors, and this is a shame from an intellectual perspective and for the whole community. But what can I do?
No, thanks. I mean, giving your opinion is a first place to start, and this is something that always just to close this and to share an anecdote. I mean, here one of the attendees is Fabien Chaz from Fourth, and he actually practically kidnapped me once when I was in Heraklion because he wanted to get Mare Nostrum failure logs. And this is true, right? So Fabian, if this is not true, you can post it on chat. So, and he did not get it, right? But anyway, data is a big issue, and but we follow up this on panel. Thanks a lot, Yves. Big applause for you, and I pass the mic to Marazakis.
Yes, so Fabian is confirming that he pushed for you to get this information. We have a 10-minute break in our schedule, so we are fashionably late in the schedule. I'm not worried yet. It's only 10 minutes. So please take a short break of 10 minutes, and then we come back with a further talk by Dimitris Gizopoulos. Thank you.
So for the ones who do not want to take 10 minutes break, our initial idea was to share a video of Budapest, 10 minutes video in Budapest, meaning that, okay, because we could not travel there, let's at least see a YouTube video. But that would probably push Zoom a bit too far. So we will just share a photo of Budapest. And let me see if I can do this. Yes, here it goes. So what you see is a parliament, Hungarian parliament. And if you think that in front of this parliament is Thames River, and this reminds me of the UK parliament, where you are thinking, well, because they're very similar. So, and I will just stop now, enjoy the view, take your coffee, do a comfort break, talk to you in 5-10 minutes. Bye-bye.
So let's get back to the session. I see that our speaker Dimitris Gizopoulos has started projecting his screen. Let's give people 1 minute to get back, and then Dimitri, you can take over. So let's get started again with our third speaker for the day, Dimitris Gizopoulos. Dimitris is a professor at the University of Athens, where he leads the computer architecture group and has quite a lot of research activity in the areas of dependability, as well as energy efficiency and performance. His talk today is about early estimation of error rates, and he's considering aspects related to software error rates and the overall masking effects of the entire system stack. I think it's quite ties quite well with the topics of this workshop. Dimitris, thank you for joining this workshop, and please take over to present your work. Thank you.
Thank you, Manolis. I want to thank you, Manolis and Petar, for organizing the workshop and for inviting me. As you just said, the topic is about error rates estimation for microprocessors. So we are moving now to the discussion about the fit rates for the components for the nodes that previously Christian and Yves were talking about. So I think it's a good match to the discussion that was held in the previous talks. This is work that has been done with my good students over the past few years. I would like to acknowledge Thanasis, George, Manolis for working with me, and it has been funded by a European project funding sources, and recently by Tetramax experiment for the tool that I will briefly talk about at the end of the talk. So the starting point is that we need to know somehow the error rate of the CPUs that are running our workloads, or GPUs or other accelerators. This applies to other chips, of course, not only CPUs. So we need to know something about the failures in time, the fit rate that these components are expected to give us when they are affected by soft errors. The discussion I'm focusing on is on soft errors, but it can apply to other types of faults coming from the hardware side. Since we are talking about hundreds or thousands of pieces of CPUs and GPUs and accelerator chips, we need to have some reasonably accurate idea about their failure rate, but also this information needs to come to us reasonably fast and early in our decision-making process. The faults that start from the hardware level, from the technology of the chips, they have to go all the way up to the different layers of abstraction to eventually affect the execution of the system, to produce errors or system failures. This means that eventually a fault, if it goes through all the layers, it can produce some failure. So this counts as part of the failure rate. Why do we need to know that? Obviously, the people I believe that are attending this workshop understand that we need to know the failure rate because we need to do error protection at different layers. We need to implement means to detect and to recover from these errors. So this means that we can either pay extra hardware at the process or the circuit level. We can implement architecture or microarchitecture level techniques to increase the robustness, to increase the resilience, and to cope with the errors. Or we can do that later on at the software level with checkpointing and rollback approaches that are typical to large-scale systems. But in all these decisions, any kind of protection we want to apply, we need to know something about the fit rate, because the cost of resilience depend on the fit rate and what we are going to pay in performance, what we're going to pay in the extra area or the energy or whatever cost we pay for. It depends on the fit rate. So we need to know as accurate as possible the expected fit rate. And this is about failures and the rates that these failures are coming. A little example, we all understand what it means to duplicate, to re-execute, to pay extra hardware cost for parity, for ECC, or whatever other means one wants to employ. A simple example here, it's a table which gives the extra storage that is needed to protect DRAMs, DRAM chips from soft errors. It can start from something as simple as a parity, which means that the extra storage cost is something like 1 or 2%, but it can be really high when more powerful techniques are applied to detect, but also to correct the errors. And this, of course, this applies to any other overhead, the performance overhead, the area overhead, the power or energy overhead, and the cost in redesign or in software and hardware redesign, these pieces. Of course, failures in time, it's a typical definition, the number of failures per 1 billion hours of operation, but I'm going to use in this discussion a typical measure that is used for microprocessor cores, for CPU chips, vulnerability to soft errors. It is the architectural vulnerability factor, the AVF, which gives the full system effect of a soft error, of a bit flip, when it happens at the lower level of a bit structure. It's the probability that an error in a bit of a structure of the CPU, something like a register file or a cache memory or a queue, whatever inside the microprocessor, will eventually affect the program execution. So the AVF is a measurement which depends on both the hardware, the microarchitecture, and the program. So it gives the full system effect of the fault. This is important to keep in mind. Having the AVF of a particular structure in hand, and also having the raw fit bit rate for the SRAM cells or the gates or the DRAM cells or whatever other technology is used, we can use this formula, the product of the fit per bit, the AVF of the structure, and the number of the bits of the structure, to eventually have the probability of failure, the fit rate of this hardware component. So when we sum up, when we add these fit rates of all these components, we eventually have the fit rate of the entire CPU. So the question is how we can calculate this AVF, this architectural vulnerability factor. The AVF, as I said, considers all the effects. It starts from the microarchitecture level. A bit is flipped in any microarchitectural component, and then it goes all the way up. Typically in the literature, other measurements, other vulnerability factors have been used. I'm showing a few here. One is the hardware vulnerability factor, the HVF, which starts from the microarchitecture, but it stops at the first time that this fault reaches an architecturally visible component. Then the discussion goes to the higher layers, to the architecture or the software layer. The PVF is the program vulnerability factor, which assumes that the fault starts at some architecturally visible component, an architectural register file, for example. And then the software vulnerability factor starts the analysis from one level higher, from the instructions themselves. So the bit flips are assumed to happen at an instruction level, one instruction at the point of time when it is executed. So this means that to save time of the analysis of simulation, for example, one can start at different points, but this is not correct, as I will be showing. In this slide, I'm showing the different approaches. One can start the analysis, for example, injecting faults, injecting bit flips, either at the circuit level, very low, the RT level, the microarchitecture level, or even higher, the architecture or the software layer. Of course, the difference is in terms of the performance of the simulation throughput, for example. If you have a very detailed model flip-flop or gate level, then you are really very slow. If you go higher, but still maintain information about the hardware, which is the microarchitecture level in performance simulators like GEM5 or others, then you are much faster, but you are not as fast as the architecture or the software layers. So one would argue that the software and the architecture layers are ideal ones to start with the analysis, injecting faults, as I said, to reach a statistically significant idea about the failures of the failure rate of the microprocessor. This is not a reasonable assumption, although it has been used a lot in the literature. I'm showing here exactly this case. These graphs are showing the architecture-only starting point. We assume that an architecturally visible point has the fault. On the right, we show that the software is the starting point, which means that a bit is flipped in an instruction. And on the right hand, on the left hand, the full stack, the AVF here, is the full story, is the full system stack from the lower level up to the execution of the full program. As you can see here, and I have several other examples, when the vulnerability of the programs, of two different programs, is compared using the architecture-only information or the software-only information, then the comparison between the two programs is the opposite, exactly the opposite in this case, compared to the full stack AVF, which is the correct evaluation. This is the correct AVF, which shows, for example, that quicksort is 2 times more vulnerable than FFT. It has a 2 times higher AVF, although the architecture-only analysis delivering the PVF or the software-only analysis delivering the software vulnerability factor shows exactly the opposite. So this is not a correct measurement because it neglects the information and the detail of the hardware. So let's now assume that I have convinced you that the microarchitecture level or the RT level, the levels that have hardware information, are the ones that need to be used. Comparing these two, obviously, the throughput of the analysis, the throughput of a simulation, microarchitecture or RT level, is huge. The difference is huge. We see here the comparison in a DSN paper published from our group and other colleagues a couple of years ago, that the throughput difference between RTL and microarchitecture level is really huge. On the average is more than 2 orders of magnitude, is 256 in this case, where we were comparing several different benchmarks, more than the ones you see here, running on ARM Cortex-A9 RTL and microarchitecture models. So RTL is detailed, very detailed, but it's impossible to run the full story. Now, assuming that we stay at the microarchitecture level, there are different options. One option is to do analytical techniques, to run analytical techniques like the very well-known ACE analysis, the architecturally correct execution analysis, which is a very fast, but very pessimistic, very worst case based analysis for the impact of soft errors on microprocessors. What we see in this diagram is a comparison of the ACE analysis in one case on an alpha processor and ACE analysis on an x86 model. This graph is from an ISCA paper from our group a couple of years ago. And on the last bar, here on the rightmost bar, you see the fault injection based derived AVF for the same component, which in this case is a register file with 80 registers. We are running the same benchmarks, and we see that the vulnerability significantly differs between the ACE analysis cases and the fault injection. And this is a fault injection campaign which is really extensive. It injects 60,000 faults in the register file. So this is very close to reality, as I will show you also later. So in terms of the accuracy of the measurement, in terms of the AVF and the corresponding fit rate, which is important for HPC systems for systems with a large number of nodes to have a reasonably accurate idea about the fit rate, the ACE analysis is really pessimistic. It provides a very pessimistic upper bound. But fault injection-based analysis is also requiring a lot of injections, a lot of experiments. What we do, and other groups did similar work in the recent past, but I believe we have a quite updated fault injector at the microarchitecture level, which is based on GEM5, very well-known microarchitectural performance simulator. And we have validated our tool on different ISAs, different microarchitectures, several workloads, etc., etc. Of course, the idea of fault injection is that the fault is injected. Then on GEM5, the workload is executed, and then the result is compared to the fault-free, to the correct result. And then the AVF is calculated as the fraction of the vulnerable cases, the cases where something abnormal happened, over the total number of injections. So only the masked cases are not included. Such programs, such injectors like our GEM5-based injector can cover a large number of hardware structures that are reasonably accurately modeled on GEM5. In our case, for example, including all the hardware components that GEM5 model includes, plus extra models that we added, extra components that we added, like different branch predictors, TLBs, prefetchers, and etc., we are able to inject fault to more than 50 different hardware structures. So the tool can provide a very fine-grained analysis of what is happening when a particular workload runs a program and faults are injected in one of the components. This is the example of the L1 data cache. You see what is happening and what is the vulnerability broken down in all the different effects for the L1 data cache. The idea is to speed up the process of fault injection. So we employed pruning techniques where we were we were pruning faults that need not be injected. And also we applied clustering, we applied classification to find similarities among faults and to run only some pilots, some representatives. Effectively, this is leading to a very big improvement in the throughput of GEM5. The effective throughput in the simulation is something like 1 million of instructions per second, which is a few times more than the baseline GEM5. This means that you can have the assessment of the fit rate, the AVF or the fit rate, in 1 to 3 orders of magnitude smaller time. So the only pending question is how accurate is this assessment? It comes faster, it comes with 2 to 3 orders of magnitude shorter time, but is it accurate? We did 2 types of experiments to prove this accuracy and to measure how close it is. This graph shows how close our assessment, the second bar in the middle in all cases, is the fit rate measurement for an entire microprocessor. This is an x86 microprocessor model from our ISCA paper a couple of years ago. Compared to the baseline here is an extremely exhaustive and extremely extensive fault injection campaign, which is impossible to run in an actual application and for all the components. You see that for all the cases, all the 3 components, register, file, store, queue, data cache, the measurement of the fit rates is very close to the baseline, to the exhaustive campaign, while the ACE analysis base is still very high, very pessimistic. Finally, the last experiment we did, and that is from a DSN paper last year, we tried to compare, this was collaborative work with a group in Brazil, UFRGS, with Paulo Reika, my good colleague from there. We took the model of A9, Cortex A9 on GEM5, where we were doing our injections. It's one of the models we can analyze. And the team from Brazil did the neutron beaming experiments on the same chip, actually implemented on silicon, running the same workloads and using also the same operating system, the same Linux kernel. what you can see in this little graph is the final result of our comparison. Gen5 injection versus neutron beaming experiment. This is the silent data corruption fit rate, the fit rate that comes from SDCs, where the primary source of the SDCs is the CPU itself. That's why I'm restricting the comparison here to the SDCs, the silent data corruptions. You see, for the values that we used for the bit fit rates, 25 is the fit rate for the beaming experiment, while 22 fit is the fault injection fit rate. This is a good indication that at least for the workloads that we run, and at least for this chip, things are very close to each other. So eventually what I'm saying, and I'm concluding with this, let's assume, I'm finishing with an example based on the previous. Let's assume that in an HPC infrastructure or whatever other infrastructure facility, we want to estimate the fit rate of a new workload. We do have some information about the workload or the workload itself, or it's a representative part of it. And then based on it, we want to decide software level software error protection, like checkpointing, frequency, or granularity, or whatever. Let's assume that we have the microarchitecture performance model of the CPU, talking about models in the previous talk by Yves. Then let's assume that we ideally have the RTL model of the CPU. That's practically not happening. And let's also assume that we have the CPU chips to beam and to do any experiment we want. Of course, let's assume we have some good part of the executable workload. So here is the full comparison of the 4 cases that I talked about. The microarchitecture level ACE analysis, it needs a few days. Let's assume 2 days in this case. The microarchitecture level injection, even with the speed up techniques that I just said we are applying, it needs some extra time. Let's say it's 5 times more, 10 days. Then the beaming, it's a fast process, but it needs to have the chips to beam. It needs to prepare the setup. RTL is out of the question in terms of the throughput of the estimation time. This is because of the very slow execution time. But what is the eventual estimation that it comes from this measurement? The microarchitecture level injection, I'm suggesting that it's really very close to what the RTL injection will give in the years of operation. It's very close to beaming. There should be some further analysis on what is missing. There may be a bit lower than this 10. I put 9 here, it may be 8, it may be a bit lower or higher, but it's still close. But the bonus in the microarchitecture level fault injection is this last box I put here. There is a fine grain analysis that the user takes, that the user of this methodology takes. You can find the software pieces that are more vulnerable than the others. You can find the hardware structures that are more vulnerable to others, so you can plan your protection techniques accordingly. And you have a fine-grained manifestation, analysis of the error manifestation. You check how many are SDCs and how many are crashes, how many hang the machine, etc., etc. So this is an extra piece of information, these microarchitecture performance models and techniques like the ones I presented here. Thanks. I'm staying with this last.
Thank you, Dimitri. Very interesting talk. So no questions yet in the QA, but perhaps I can get people warmed up. So there is this difference in the manifestation of errors. You brought it up yourself. So we can have a mostly benign crash. So and I can also have a silent corruption of state. So do these techniques actually take into account this type of difference in how a problem can manifest itself? Is it even reasonable to be, assuming that there is a way to distinguish?
There is a way to distinguish if you are working at the simulator level. And of course, there is a way to distinguish when you're running in an actual system. There are several soft errors that can eventually lead to a silent data corruption, which means that the fault is not detected. There is no way to detect it, but only the output is corrupted, which means that you need to compare against the golden, the fault-free output. To me, it makes really good sense to have this granularity of the analysis, because it's completely different when you have an SDC and the user of the system gets the result, but it is corrupted, as opposed to system crashes or to other types of application crashes.
Okay, thank you, Dimitri. And in the prior slides, you showed us that you have taken into account, for example, the registry file, the data cache, etc. Is there some limitation for applying the technique? I mean, in principle, I could, I don't know, disrupt the branch predictor, just to give an example, or the instruction cache, right? Can you provide, let's say, possible advantages and disadvantages of the techniques for different types of the architectural modules, of the hardware structures, actually?
Yeah. That's a good point. One weakness of staying at the performance models, at the microarchitectural performance models, is the missing pieces of the hardware. And as we all know, Gen 5 and other performance models are quite fast because they are not modeling the entire hardware. The complex state machines, for example, or combinational hardware like the ALUs, they are not modeled. They are simply modeled as functions. So you don't have a accurate way, accurate from the hardware point of view, to model the errors in these components. So the question and the open discussion in this research direction is how much is the contribution of the combinational models or the state machines that are not modeled on Gen 5 with the accuracy of the hardware bit in the overall vulnerability. I'm suggesting, I am guessing that the contribution is not that big. So all these components that you see over here are the biggest contributors to the vulnerability of the microprocessor. Now, talking about the branch predictors or the prefetchers or the instruction caches, I don't know if your question was heading this way, but there are cases where the components have some self-correcting nature and they don't lead to failures. They just, faults on them just lead to timing errors, to performance faults, to loss of performance. And this is part of a study that we recently did on branch predictors. When you inject soft errors, even hard errors on branch predictors, then they are self-correcting, of course. They change the prediction and the operation continues correctly, but you're losing performance. How much is this performance that you lose is another aspect that can be used from these tools, from this tool of ours and other similar tools.
Thank you, Dimitri. Actually, I was going to follow up with that, and likewise the TLB, for example. There are hardware structures that are, let's say, less destructive if you get a disruption there, and there are others that are quite, disruptive to have a problem. Correct. So I understand that the method can be applied, and but there are all sorts of, let's say, peculiarities, sorry for using a non-technical term for that, depending on the unit itself. But still, I mean, I fully agree with your approach and for the motivation for the approach and the benefits that this type of approach can provide. I'm just bringing up the complexity. I mean, a modern processor is really complex and all sorts of things can happen at the same time. I'm not just disrupting one aspect of the chip, perhaps I'm disrupting several of these. So also what happens if I have issues with my load store unit and my instruction cache and my TLB? I don't know, perhaps I'm paranoid, but No.
You're not being paranoid. It's a very meaningful question, and the answer is as simple as that. We have considered additional scenarios like the ones that you mentioned. The tool itself, this JFIN fault injector, can inject faults in all different pieces of the hardware. You can select 2 or 3 or 10 different pieces, and you can assume that they have some malfunction. A soft error is very unlikely to affect more than one of them. but it is likely for a soft error for a particle that strikes the CPU silicon to affect more than one bits that are close to each other. So this is a very useful additional case study that we have done. We have done multi-bit upsets like the cases that Christian mentioned at the beginning that are very likely to happen in dense arrays in CPUs and GPUs. So what is the fit rate when double or triple or more bits are flipped by a single particle strike? That's an important case study that we implemented, and it was published a year ago in the Workload Characterization Symposium. And the last one, also related probably to the question that you asked, is a study that we recently implemented, performed in the tool, that assumes that the system is undervolted, the voltage is reduced. So we deliberately add resilience issues, reliability issues to the CPU. There are components, the ones with speculative nature, the branch predictors, for example, that can tolerate a large area of undervolting, where in this area of undervolting, several faults happen, which are permanent faults. So the question would be, how much power and energy you save from the undervolting, you reduce the voltage, but how much time, thus energy, you lose because the predictor has a lower performance. It predicts with a lower accuracy. So there is a sweet point that you can play for the different predictors, and you can evaluate which is the best predictor when you have an undervolted system in your facility. There are tens of different case studies that can be analyzed in a tool like that.
Thank you, Dimitri, for pointing out these extra dimensions. I think we can pick it up again in the panel. Let's proceed with the next speaker in the schedule. Isaac, can you set up, please? Yes.
Sure.
So I hope that I'm pronouncing your name properly. I'm reading it as a Greek, Isaac.
Isaac, yes,
okay.
right.
Yes.
That's it, yes.
Boixaderas. Isaac is a research engineer at BSc, working in the memory systems group, and will be presenting work on the topic of cost-aware prediction of uncorrected DRAM errors based on studies of operational logs from the Mare Nostrum machine clusters. I think it's also a quite important collection of data from the field, and likewise an analysis related to that and the cost-benefit aspect. Isaac, please proceed to show us your material and explain the topic. Yeah.
Yes. Okay. I think you should see my screen now.
Yes. Yes. Thank you.
Perfect. So good afternoon, and thanks for inviting me to give this talk. My name is Isaac Boixaderas, as he just said, and here I'm presenting the work done in Persona Supercomputing Center related to cost-aware prediction of uncorrected DRAM errors in the field. First, we have to distinguish between corrected and uncorrected DRAM errors. In high-performance computing, main memory is protected with error-correcting codes that can even handle cases where an entire DRAM chip is corrupted. If the DRAM error is corrected, the failure doesn't propagate further from the memory controller, but as data correction is performed in parallel with data read, corrected errors effectively have no impact on system performance and reliability. However, if the DRAM error cannot be corrected, then the whole HPC job has to be terminated, typically losing all CPU hours since the last checkpoint. These errors are known as uncorrected errors, and they have an important impact on system reliability and availability. Uncorrected errors in main memory cause around 50% of all hardware failures, being especially problematic in HPC systems, where a single job typically executes for hours or even days in thousands of nodes. Therefore, memory systems reliability is an important limit on the ability to scale to larger systems. The main objective of our study is to predict DRAM uncorrected errors before they occur, and to take active measures to mitigate its negative impact. In order to predict forthcoming uncorrected errors, we use preceding events, for example, corrected errors or DIM characteristics, such as manufacturer or chip capacity. In our study, we compare 6 machine learning classifiers, that is a random forest, gradient boosting decision tree, Gaussian naive-based logistic regression, support vector machine, and a deep neural network, and we report the results of an error prediction method based on random forest, which in our case showed the best performance out of the 6 classifiers. With our method, we were able to predict up to 42 out of 67 uncorrected DRAM errors, which correspond with a reduction of lost compute time of 57% and net savings of 21,000 node hours per year in Mare Nostrum supercomputer, which is one of the largest HPC systems in the Partnership for Advanced Computing in Europe. It comprised at the time more than 3,000 nodes and more than 25,000 DIMMs. Our method is trained and evaluated on memory error logs during the production period from October 2014 till November 2016. And during that period, the system registered close to 4.5 million corrected errors and 333 uncorrected errors. We have to take into account that only a small fraction of uncorrected errors have an impact on system reliability. That's because uncorrected DRAM errors, as many failure events, appear in bursts. In a burst of uncorrected errors occurring in a short interval of time on the same node, only the first one has an impact on system reliability, as it is the one that causes the job termination. In our study, of the 333 detected uncorrected errors, only 67 of them have an impact on system reliability and are therefore using for the evaluation of our method. We perform predictions periodically. The prediction interval is the time between successive prediction moments. We propose a triggered prediction method where predictions are scheduled at regular time intervals corresponding to T1 to T4 in the figure. But the prediction will only be made if the preceding prediction interval contains one or more trigger events, such as corrected errors, uncorrected errors, or node boots. In this figure, a prediction will only be made at T3, triggered by the events detected in the interval between T2 and T3. The prediction window refers to the length of the future time interval for which a prediction is made, and the observation window refers to the length of the past period that is observed in order to make the prediction. In general, the longer the prediction window and the higher the prediction frequency, the higher the number of UEs that are visible to the prediction model. But there is, however, a nonlinear increase in the number of predictable uncorrected errors and a point of diminishing returns. So taking into account multiple factors, in the study we select a prediction window of 1 day and a prediction interval of 1 minute. The input variables of our model, usually referred as features, are obtained directly from the logs corresponding to 3 different levels of the system, that is DIMMs, sockets, and nodes. For each one of them, we derive features related to corrected errors or uncorrected errors. In the case of DIMMs, we also use features that describe the DIMM characteristics, such as manufacturer or chip capacity. And for the nodes, we include features related to their reboots. We formulated the DRAM error prediction as a binary classification problem. The variable we want to predict answers the following question. Is there going to be an uncorrected error in the node in the following prediction window? And this is either yes or no. Machine learning classifiers estimate the probability that the sample belongs to each of the 2 classes. We classify the sample as negative if the probability of belonging to the negative class is lower or equal than a certain threshold, known as the decision threshold. Otherwise, it is classified as positive. In our study, we explore different values of the decision threshold and show its impact on the results. As we are dealing with a binary classification problem, there are 4 possible outcomes. We either have a true positive, when we predict that there is going to be an uncorrected error and it indeed occurs, a false positive, when we predict there is going to be an uncorrected error, but none occurs. False negative, when we don't predict an UE that really occurs. Or a true negative, when we don't predict any uncorrected error and none occurs. In our cost-benefit analysis, the saved node hours are determined as the difference between the cost of not applying any prediction method and the cost of applying one. In the case of the cost without prediction, we calculate it as the number of UEs that occurred on the system times the UE cost. For calculating the cost when using a prediction method, we add the total cost of performing error mitigations plus the total cost of non-predicted UEs plus the cost of running the prediction method. And this last one in our case was negligible. The impact mitigations overhead should be counted each time the model predicts an uncorrected error, independently of whether the prediction is a true or false positive. A recent study analyzes various actions that can mitigate the impact of node failures, such as live job migration, node cloning, and checkpointing. And the authors conclude that 2 minutes are sufficient for most of these actions. Therefore, we consider that the overhead of a single impact mitigation is 2 minutes. When there is an uncorrected error, it incurs a certain cost that depends on how long and on how many nodes the job is running at that precise moment. To cover HPC systems of different scales, we perform sensitivity analysis and consider average UE costs of 5, 50, and 500 node hours. And we also show results for the real distribution of HPC jobs executed on Mare Nostrum for production. The results obtained with the cost-benefit analysis show a big difference in the saved node hours when considering the different uncorrected error costs. For a small UE cost of 5 node hours, UE prediction has 0 effect on the saved compute time. We are going to explore the reasons in the following sections. For a UE cost of 50, the saved node hours increase to 586 node hours. For large UE cost of 500 to more than 16,000 node hours. And the net savings computed based on the production job logs of Mare Nostrum 4 reach 42,000 of saved node hours, or with the same 21,000 node hours per year. Other studies report uncorrected error rates that in some cases exceed hours by up to 3 orders of magnitude. In these systems, the UE cost and saved node hours would increase in proportion. In order to go a bit deeper in our analysis, let's analyze the influence of the decision threshold on the 2 main factors of our cost benefit. That is the number of UEs we can predict and the total number of impact mitigations performed. As it would be expected in the case of correctly predicted uncorrected errors, the lower the decision threshold, the more correctly predicted uncorrected errors. Going from 42 predicted uncorrected errors with a threshold of 0 to 0 predicted with a threshold of 1. In the case of the total UE impact mitigations performed, that is when our model's outcome is a positive, we can see that the impact mitigations go down as the decision threshold decreases. For small values of the decision threshold, there are up to 250,000 mitigations, which is almost 4,000 impact mitigations per uncorrected error. The two figures clearly show that varying the decision threshold provides a trade-off between the true positives and the total number of positives. The more uncorrected errors that we predict, the more UE impact mitigations we perform, and vice versa. Deciding which option of this trade-off is preferable depends mainly on 2 factors: the cost incurred each time we perform an impact mitigation, and the cost of not correctly predicting an uncorrected error. In order to analyze the dependency between the cost benefit and the decision threshold, we show the saved node hours for different uncorrected error costs when varying the threshold from 0 to 1. For a UE cost of 5 node hours, the relatively large number of false positives mean that the optimal decision threshold is 1. So the model never suggests an error mitigation, and the only loss is the model overhead of a few node minutes. As the threshold is reduced, the model losses increase, reaching 8,200 node hours for a threshold of 0. This is due to the cost of false positives. For an UE cost of 50 node hours, the optimal threshold reaches a plateau around the value of 0.7 with a few hundreds of saved node hours. The model efficiency drops especially as the threshold decreases. For an UE cost of 500 node hours, the model reaches the highest savings for the decision threshold of 0.09, with a sharp decline on both sides. In this case, a good threshold selection saves thousands of node hours. Finally, for the job size distribution from Mare Nostrum for production, the optimal decision threshold is lower, with a value of 0.02 and net savings of 42,000 node hours for the 2-year period of our logs. To further explore the dependency between the uncorrected error cost and the decision threshold, we analyze the optimal threshold as the UE cost varies between 5 and 5,000 node hours. We can see 3 different main areas in this figure. For small UE costs, the optimal decision threshold equals 1, so the system should not perform error mitigation actions because the overhead would exceed the benefits. For large UE costs, the optimal threshold converges to 0. In this case, the system should perform error mitigations whenever triggering events are detected. And in the area of the moderate UE cost, that is between 10 and 1,000 node hours, the prediction is more complex, requiring proper prediction methods and careful threshold selection. Next, we evaluate our prediction model using standard metrics, such as recall, precision, and F1 score. Recall is the ratio between the number of correctly predicted and corrected errors, that is the true positives, and the total number of uncorrected errors, which are true positives and false negatives. For a threshold of 0, the method predicts more than 60% of the uncorrected errors, but note that we cannot predict some of them because they don't have any preceding event. The precision is the ratio between correctly predicted UEs, so true positives, and the total number of predicted UEs, which are true and false positives. In our case, the dominant factor for the calculation of the precision is the large number of false positives, which leads to small values. F1 score, as the harmonic mean of precision and recall, is dominated by the low precision numbers, and it practically matches the precision curve with slightly higher values. Here we can see on the left the saved node hours for UE costs of 50 and 500 node hours, and the recall and the precision on the top and bottom right, respectively. There is nothing in the standard metrics in precision and recall that indicates which is the optimal decision threshold for different UE costs, or that the net benefit for large UE cost is high. This is because recall doesn't consider false positives, which incur costly mitigation measures when they are not needed. Precision puts the same way on different prediction outcomes, that is true and false positives, whose costs differ by orders of magnitude. Also, it does not consider false negatives, which may have a very high cost in this case. Overall, these standard prediction metrics are insufficient to decide whether and for which parameters the prediction is useful in practice, and we would suggest to complement them with cost-benefit analysis in future studies. Our study presents and evaluates a method to predict DRAM uncorrected errors, and after comparing 6 machine learning classifiers, we use a random forest classifier, which is trained and evaluated using error logs from more than 2 years of production Mare Nostrum 3. Our cost-benefit analysis shows that the prediction method reduces the lost compute time by up to 57% of a real production workload mix, which is a net savings of 21,000 node hours per year. Our prediction method source code is released as open source under BSD3 license in the following GitHub repository. And our cost-benefit analysis shows that the effectiveness of our prediction method is highly dependent on the system and workload characteristics, pointing the way to future work on adaptive resiliency techniques. Overall, we hope that future researchers will build in our work to improve the throughput of production HPC systems, as demonstrated by a clear cost-benefit calculation. This concludes the presentation, and I'm available for questions.
Thank you, Isaac. Are there questions in the QA? Not yet.
Yeah, let me check.
Not yet. Well.
So sorry, Manolis. Before you continue, I mean, there is very important thing that Isaac forgot. Yes, terrible. I mean, it's and in addition to being one of the most powerful supercomputers in Europe, Mare Nostrum is by far the most beautiful one, but by far. So I mean, it is located in a chapel at the campus at UPC, Polytechnical University of Catalonia, and BSc. But this is just bragging around it. What is important info for the audience is that you can actually visit it. You can enter there and you can take photos or whatever. And I think this is one of the best hidden gems of Barcelona. And actually the chapel actually is also some pieces of the book of Dan Brown. What is the name of the book, Isaac? Do you remember?
The Origin. It's The Origin.
The Origin. Yes. The Origin. It happens in this chapel. So I mean, this will be a famous place. So please visit it while the entrance is for free. This is good, right? So that's it. Sorry, Isaac, but it's, and if you want to visit it, you can, whenever you come to Barcelona, just send me the email and we will make it happen. So that's all from my side. Well done, Isaac, as always. Thanks.
Thanks, great. I see we have a question in the QA.
Yes. Yes, please. So the question is, did you consider other inputs to your system, such as temperature, memory loads, etc.?
No. Well, in our paper that's already published, there are listed the features we used, but unfortunately we didn't have logs for temperature, for example, as we didn't have logs for the workload or the system at that time. So we couldn't make the prediction with all the logs we had, but however, you can find the full list in the paper.
Right. There is another question that I received from private chat. It's, did you accelerate the generation of correctable and uncorrectable errors, for example, by deliberately under refreshing your DRAMs, or is it like let's say full spec system and you just pick up the information from the operation logs? So is it like a controlled study, or is it an observation?
I think
the question comes from Dimitris.
Better than me.
Okay, yeah, so you're throwing with me. So I will tell you, I'm here like on standby for two reasons, and it's not because I know some things more than Isaac. Maybe I'm more on the computer architecture side, but even more important to make sure that we say what we can say. And this is, no, so the question that Manolis said, no, this is production analysis, right? So there is no undervolting, okay. There is no under refreshing. Right. No, this is production, right? So this is what you get. And this also means that, and this is actually what we see, that it is a very stable system, which makes it not trivial to analyze. It is much easier to analyze something that has like, undervolting or under whatever, then you have much more errors. But this is real life, as real as you can.
That's fine. A further question in the QA, do you have a number about the overhead of the prediction mechanism? I guess the rationale is if we can apply it, in a production environment rather than as you do now, which is after observing the events. So yes. What could be the overhead for your techniques?
It was in the order of 9 minutes. I mean, for the training and predicting, it was quite fast, especially because we performed undersampling, because we had a lot of data regarding the errors, but not that much data for the errors regarding the uncorrected errors. So with the undersampling, we could reduce a lot the number of data we were fitting to the model. This also comes at a cost with false positives, as you just said, and you just saw. But that's it. It's order of 9 minutes, so it was not. You don't have to worry about this.
Okay, Isaac, thank you.
Thank you.
No other question in the QA. I guess we can pick up this discussion again in the panel. So let's thank the speaker and let's proceed to the next talk in the schedule by Manolis Ploumidis. Manoli, please set up your presentation for us. And the topic, now Manolis Ploumidis is a postdoc researcher at Forth in Greece. His topic is research allocation for MPI parallel jobs in the presence of failures. And he's going to present a summary of his recent research here at Forth. Manolis, you can start your talk, please.
So, hello all. My name is Manolis Ploumidis. I am affiliated with the Foundation for Research and Technology in Greece. And the title of the talk is Resource Allocation for MPI Parallel Jobs in the Presence of Node Failures. And this is a joint work with Yannis Vardas and Manolis Manzakis. So the structure of my talk will be as follows. First is the introduction with the motivation and the contribution of this work. Then is the methodology, which includes the system model, the fault model, and the description of the proposed approach. Then is the evaluation, and finally some conclusions and a description of our future work. So HPC systems grow in size to meet the increased demand for both capability and capacity, and these systems are served by multiple users and their concurrent jobs. Access to these shared resources is coordinated by systems known as resource managers and job schedulers. And apart from access to resources, these systems have other goals like improving system utilization, providing fairness, improving performance and reliability. And a well-known such system is LARM. In this work, we focus on the performance of MPI parallel applications. And for that applications, apart from the time spent for computation and communication, a significant contributor to their completion time can be the restarts required due to node failures. Needless to say that failures waste system resources also. A common approach for improving the performance of MPI application is to assign resources to processes of that job in such a way that communication cost is minimized. And the rationale is to try and play processes with a heavy communication profile on nearby nodes. So in this work, we discuss a resource allocation approach that, apart from the communication cost, it also targets another contributor to job completion time. That is time that is wasted because of job restarts that are due to node failures. Let us also note that our approach has also been integrated into SLARM. The system model used is the following. We have the topology described through graph edges, where vertices correspond to nodes. Edges denote the paths between each pair of nodes, and the weight is the cost for traversing the path, and the cost expressed in number of links. We assume a 3D torus topology with fixed routing. Our approach also uses a second graph as input, which is the communication graph, that the goal is to capture the communication pattern of the target MPI application. It is derived through a custom profiling tool by a trial run of the target application. And what it captures is the number of bytes the traffic exchanged between each process pair. The fault model assumes the following. With the term failure, node failure, we note any hardware or software related event that constitutes a node temporarily unavailable. When a node is in the failed state, it is not able to send, receive, or forward any traffic, nor it is able to reply to any heartbeats. We further assume that a reboot is enough to fix the error and that it incurs zero recovery time. And finally, we do not assume the presence of any checkpoint restart mechanism, which means that when a job is aborted, it is restarted from scratch. The goal of the proposed approach is to derive an assignment of platform resources onto processes of the MPI job. In other words, the goal is to derive a mapping of the communication graph denoted as G onto the topology graph denoted as H. And for that, we use node failures to post-process the topology graph. At this point, I should also note that our approach is heavily based on the Squatch graph mapping library for solving the corresponding graph mapping problem. In our work, we derive 3 different variants of the proposed approach, which implement 3 different policies. The first one is the failure oblivious variant, which completely disregards node failures while selecting the nodes to be used. And precisely it selects the first k consecutive and available nodes to form a new description of the topology, denoted as H oblique here. The second variant is the pessimistic, that tries to find a continuous and rectangular part of the topology graph with the minimum possible number of failure-prone nodes, and failure-prone node is denoted a node that has non-zero failure probability. And finally comes the weighted variant, which simply assigns larger weights to paths that pass over failure-prone nodes. For all three variants, the mapping of the communication graph G onto one of the topology of the post-process topology graph is handled with the Scott's graph mapping library. Let us go back a bit to the motivation for our approach, and this slide captures one of the scenarios that we have simulated. It depicts a topology, a platform that consists of 1,024 nodes arranged in a 16 x 8 x 8 3D torus. We assume that we are going to allocate resources for an MPI job with 256 processes. All nodes are available, none of them is occupied. And in this scenario, we assume that 21 nodes have a non-zero failure probability, and these nodes are denoted with a red circle. So on the bottom of the slide, the green box includes the nodes that are to be selected by default resource allocation policy of SLARM. So SLARM is going to select some nodes that are marked as failure prone, while the black box on the top part of the figure shows the corresponding node selection that is performed by the pessimistic variant of the proposed approach, which takes into account node failure. So it tries to identify a part of the topology that does not contain such nodes. Before listing the benchmarks that we used for our evaluation process, let us discuss some benchmark parameters that affect the quality of the mappings that are produced. The first parameter is the ratio of the computation to the communication time. Our approach targets, one of the goals is to minimize the communication cost, so its benefit is expected to be higher for applications that are communication intensive. The second parameter is the ratio of point-to-point and collective traffic. Again, the benefit is expected to be higher for applications that have more point-to-point traffic. And the reason is that for collectives, it is less frequent for specific process pairs to have significantly higher traffic than others. And the third parameter that is important is whether the communication pattern of the target API application, whether it can be characterized as regular or irregular. And at this point for our study, with the term regular, we characterize a pattern where a specific rank has significant traffic with nearby ranks. And this pattern is similar for all ranks. And the reason why this pattern is important is that if each rank has traffic with some nearby ranks, then it is highly probable for SLARM to place these ranks on nearby nodes, and thus they will experience reduced communication cost. The benchmarks that we use in our evaluation is LAMS, which is a state-of-the-art molecular dynamics code. From the NAS parallel benchmarks suite, we use the data transfer one. We derive the traffic heat map through a custom profiling tool. And for both benchmarks, we have noticed that the largest portion of the total execution time is spent for communication, so there is potential for improvement. The ratio of traffic through point-to-point primitives is 100% for the DT transfer and 73.4% for the case of LAMPS. And finally, through a visual inspection of the heat map, the DT benchmark exhibits an irregular communication pattern, while LAMPS a more regular one. In this slide, we list the two heat maps produced. The leftmost part corresponds to the heat map for LAMPS, and the rightmost for the DT one. And as we can see for the LAMPS benchmark, let me also note that darker data points correspond to higher traffic. So we can see that there are a significant number of data points arranged along the main diagonal for the case of LAMPS, which means that there is traffic among the nearby ranks. While the pattern is quite different for the case of the DT benchmark, where there is no traffic along the main diagonal, and each rank has significant traffic with nearby ranks, with distant ranks. So, as far as our evaluation method is concerned, we rely on the SimGrid distributed system simulators, and a key advantage of SimGrid is that it allows to simulate unmodified MPI applications. Another advantage is that it also allows to provide a detailed description of the topology studied, both in terms of nodes and the routes followed for each pair of nodes. Another interesting characteristic is that it allows to set the capacity of a specific link to 0, which means that every traffic that is traversing this link will be erroneous. And this is actually the feature that we exploit in order to emulate a node as being in the failed state. We set the capacity of all the links that this node belongs to 0. We have simulated 5 groups of scenarios, with each group corresponding to one batch of 100 identical instances of the same application. For each group, we select a random set of nodes to be emulated as failure prone, with this set being set to 2% out of total nodes. For each simulated scenario and each node in the aforementioned set, we see that the probability of that node entering the failed state in one scenario is 2%. The topology explored is a 3D torus with 124 nodes. The number of processes involved in the lamps is 256, while for the DT benchmark is 85. And the performance metrics that we use are the batch completion time and the fraction of jobs that are aborted due to some failure. Let us also note that for batch completion time, whenever a job is aborted due to one or more failures, batch completion time is augmented by an interval that is equal to having a successful run of that job. The plot in this slide captures batch completion time for the case of the DT benchmark. On the horizontal axis, we have the batch ID, while on the vertical axis, we have the batch completion time in terms of seconds. And actually, in this plot, we compare the 3 variants of the proposed approach with the default resource allocation policy of SLARM, with SLARM corresponding to the light brown bar. And as this figure shows, the pessimistic variant of the proposed approach, which is the light blue bar, achieves the lower batch completion time compared to all resource allocation policies. More precisely, the pessimistic variant achieves 67% lower average batch completion time when compared to SLARM. The failure oblivious variant, the one that disregards failures, has 9.3% higher average batch completion time when compared to the pessimistic variant. And it is also worth noting that the pessimistic variant also manages to reduce the number of jobs that are aborted, with the corresponding job abort ratio being 0.8% for the pessimistic variant and 5.6% for the case of SLARM and the failure oblivious variant. The figure in this plot depicts the corresponding plot for the case of lamps. Again, on the horizontal axis, we have the batch ID, while on the vertical axis, we have batch completion time measured in seconds. The light brown bar again is SLARM, while the blue bar is the pessimistic variant. And again, we can see that for almost all batches, apart from batch number 1, the pessimistic variant achieves a lower batch completion time compared to the other schemes. Again, compared to SLARM, there is a decrease of the pessimistic variant achieves 34% lower average batch completion time. The failure oblivious variant is 7% exhibits 7% higher average batch completion time. And again, it's notable the decrease in the ratio of jobs that are aborted. It is 5.4% for the case of the pessimistic variant, while the corresponding value is 12.4% for the case of the SLARM and the oblivious variant. And at this point, I should also note that for both benchmarks, for both lamps and the DT benchmark, the weighted variant achieved the largest batch completion time. And the reason is that Scotch fails to avoid paths that have failure-prone nodes. And let me remind that these paths are the paths that are assigned larger weights. So Scotch is not able to avoid these paths and assign processes on nodes that pass over these paths. And a final point, it is interesting to compare the benefit of the proposed approach between lamps and the DT benchmark. Let me go back a few slides. The corresponding benefit for the case of the DT benchmark is 67%. And please recall that the DT benchmark is the one that exhibits the irregular communication pattern. while this benefit is a bit reduced, is 34% for the case of the LAMS benchmark. So let me skip the takeaway results. Maybe I'm running out of time. So allow me to list as quick as possible the part of our future work. In the current work, we have assumed the 3D torus, so we want to adapt to a more complex torus topology like a 4D one, and especially adapt the heuristic that selects the continuous and rectangular part of the torus that's less probable to fail. We have assumed for that initial part of our study, we have assumed some fixed numbers for both the number of the failure pronodes and the failure probability. So our next step is to update and parameterize the fault model, maybe and fail model inter-arrival failures with distributions like Weibull or exponential distributions. And these are the two distributions in the literature that I'm aware of that are supposed to best capture the failure intervals. And also to try a model for selecting the numbers that are emulated as failure prone. Other interesting parts is to remove the assumption for zero recovery time and also explore the interplay with of the resource allocation approach and the scheduler. In the scenario where you have a queue that is full of jobs, so you want to allocate resources for multiple jobs. And also there is another point, maybe I don't have enough time to discuss, the minimization of the communication cost and whether it's better to perform the process placement approach or ignore, override the process placement and just optimize the heuristic, the collective algorithm that runs on top of the topology. And with this, I would like to thank you for your attention.
Thank you, Manoli. There is a question in the QA box. Do you think your approach would be suitable for other topologies, for example, Dragonfly and Fat Tree? To rephrase, is it, let's say, too specific to the torus topology?
Currently, the work is more focused on the torus topology. It could be, and the problem is that some nodes also serve as relay traffic for other nodes. So for the torus topology, you just have the nodes that send or are destination of traffic. So it would be more difficult. The quick answer is that maybe the only thing that you could do is try and avoid allocating nodes that again are highly probable to fail. But it's a bit more difficult to take into consideration the probability of the switches failing. So it's more complicated.
Okay. I see no further question in the QA. Petar, do you have a question from your side?
No. Did I do something that makes you that I have one?
I always feel that I should ask you. You think big thoughts, so well, you know. Yeah.
Yes.
So,
you're right.
Manoli, thank you for the talk. The next speaker is Petar, and he's wide awake, as we all saw. So let's proceed with the next speaker.
Thank you, Manolis. So so let me share my screen and yes. Here it is. Do you see my screen now? Full presentation mode?
Yes, it is full presentation mode.
Great. Thanks, Manolis. So I did notice that you did not go over my curriculum, but that's fine, right? I mean, that's fine. Okay. I did notice that. I did know. That's fine. Keep moving, right? That's okay. So yes, I come from Barcelona Supercomputing Center. But the work that I will talk about today is not presenting only the BSc. It presents a group of people that I don't even know how to define. A group of people who defined about a problem, and a group of people who is trying to understand how to solve the problem without claiming that we have a solution for it. And the problem is somewhere around resilient HPC systems, but with this flavor that European. And European, I mean made in Europe. Because if you're not aware of, Europe has a lot of initiative to build its own HPC system, its own HPC hardware, coming from processors. I mean, starting from processors, going all the way to the exascale. And resilience is one of the aspects that we brutally ignored. So this is what we will talk, what I will try to cover. So there are a couple of questions that we should answer. I will try to answer. Now, number one is, who are we, right? I told you it's not BSc, just a bunch of guys. What did we do? What do we want to achieve? And there is a question for the audience and for everybody here is, how can you help? Because if you're listening to this at 7 p.m. in Europe and you're involved somehow in resilient work, then we really need your help. It means that you're part of this community. And I even personally think that it is your job, it is your responsibility to help us really make resilient HPC systems, and again, with the flavor of European trademark. But before going there, before going into these questions, I have to do a step back. And we have to really think, can we agree on the fundamentals? And can we set some foundations for our work? So, I mean, there are two big issues with HPC resilience. And you could feel it even in the workshop today. And this is well known, sort of well known. But maybe we should be even more explicit about this. One is this: resilience is a vertical problem, and it requires holistic solutions. And if you were listening the workshop today, you could see that. You could see Dimitris talking about resilient issues at the level of the chip, and you could see Christian talking about the largest supercomputer in the world. And resilience has problems on both sides, both scales, and everything in between. So this is the way I like to illustrate this. And this is one document that talks about resilience. It is DOE, right? So, and you see, for example, in the table of contents, you see in the hardware challenges, fault tolerance. Then you see in the programming models, again, it was listed as one of the challenges to exascale. And then at the compiler level, and then at the runtime, and you can find it everywhere. Another important thing that is not maybe as explicitly stated as it should be, that resilience in its many aspects is all or nothing problem. And what do I mean with this, right? So this is a tire. This is a flat tire, right? This tire will not get you to work unless you work from home. So, but if you take a look at this tire is still 95 or 99% good tire. You know, here is good, here is good, here is good, here is good, here is good. But you don't need 99% good tire. You need 100% good tire, or you have a problem. The same thing happens with resilience. I mean, all you have a solution that makes a resilient system meaning HPC system, or you have nothing. You cannot say, no, we are super resilient in our caches, but we do nothing about memory. Or no, we have good memory and caches and the whole data path, but interconnect. Why should we care about this? So this is very important. And it is very important, especially for Europe, that is trying to build exascale HPC systems, or at least building blocks for them. Because a lot of projects that we have, and we have a lot of projects that are trying to do so, give us some pseudo 20% resilience approach, which gives us a tire like this. You know, this tire is 20% good, at least. You know, so it's good here, it's good there. It's also not terrible here, but it's useless. And this is something that I think we should all face and say, okay, so what do we do about this? Good news is that a lot of people in Europe agreed that the problem exists. And the thing is, in Europe, we do have a lot of R&D on resilience. We have seen great talks from people who are working decades in this area. But all of them separately will not solve the problem, will not make us resilient HPC with European trademark. And it was very easy. I'm very happy that when I talked to these people, we got very positive feedback from all of them. saying, yes, this is precisely what we need. We have to think holistically. We have to unite. We have to think how all these bits and bytes that we care about make something great together. So this is how it started. And this group of people exists. There is a mailing list. We talk and we have some outcomes and we have some vision. Interestingly, this group of people, they were already working in a lot of European projects that tackled resilience problem. But the only thing, so the knowledge is there, experience is there, funding is there or almost there. But we have to unite and we have to do this together. And we have to make 100% resilient system, not 20% or 30 or 85. Okay, so what was our idea? I mean, what do we have to do? And we said, first, we have to set foundations. And these foundations have a couple of points. I will be super brief on the technical side because it's late and then I want to have a dinner at some point. So step one of these foundations is we have to understand the resilience-related characteristics of HPC systems and applications. What does it mean? We had a talk from Isaac about DRAM errors in the field. Do we know what is the cost of this error for BSC, for example? Do we care about them? Should we care about corrected DRAM errors or only uncorrected DRAM errors or both? How big is the problem that we try to solve? And we don't know this. We don't know this, and it is maybe resilience is not the best thing to announce of your system, because the only thing that you could announce that it fails from time to time, and nobody likes to say that. You don't even maybe have the logs. You definitely don't want to release the logs. So this is the first thing that we should sit and agree. Second thing is we have to start from state of the art, but not state of the art like let's read ISCA papers, but state of the art, what do we have in Intel-based or AMD-based or IBM-based systems? Christian was talking about Cray. I mean, and how these guys are doing their systems forever. And then if we want to build something that will eventually compete on the market with these systems, we have to be aware that these systems are gold standard for us. Everybody is going to compare us with them. So if they have some feature and we don't have it, that's a great opportunity for us to be kicked out of a HPC system tender. Number three, set a priority for everything we want to do. Because yes, funding is always limited, true. So let's start with the most important things. And this is something that is not easy to do, but it is something that we as a community should do. And then as setting a priority, something that we defined is the list of the must-have HPC resilience features. And in particular, we did focus on CPU, memory, and FPGAs because this is the piece of the hardware that we were developing. But we're moving towards the whole system, and I hope that soon we'll have more inputs. So here are this is the list of these must-have features. And you can slowly read, just start reading, no need to read everything in detail. And you will see nothing new here. Actually, all these features are old. They're with us for at least a decade. But it is a very important subset of everything that we have now in, for example, Intel systems. And what we did as a group of 30 experts from 15 European projects, plus invited external experts, right? We said out of those 100, we will select those 10 or 12. And this is where the money should go first. Once we do these 12 issues, then we keep moving. Then we keep talking about research and improving state of the art in terms of ISCA or whatever publication. And this checklist is very important for European projects in HPC from the point when you submit the project to the point that this project is reviewed. Because this list is essentially a scoreboard saying, okay, So you have to go from one feature and to say, I have this one, I have this one, I have this one, I have this one. Taup, maybe I should do something about this one. And you can read, you can find this list, you can find all the rationale behind it. You can find a lot more stuff about our view of what resilience should be in this document. It's publicly available. It's a white paper. Go check it. A lot of people contributed to this document. A lot of people reviewed it. I'm very happy that this happened. And I think that this was really needed to set some foundations for everything we do in future. So at this point, you may tell me, and I have heard this many times, yes, but this is not research, right? And you would be absolutely right. This is not research, at least not how we typically perceive it. But the work that we did is important, missing, and useful. Important because you know the importance of resilience. If you don't have resilience in your potential HPC system, nobody's going to buy it. It was missing. Again, the EU-funded research on resilience was scattered and unconnected. And what we did is useful. It tells us where are we in terms of resilience with respect to state of the art. For example, with respect to the US or Asia. And it provides a clear scoreboard. I showed you tick, 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 taup of the features that you should incorporate in your prototypes, pilots, production systems, and makes you think about this from the project proposal until the final review. We have heard today, I think that Christian said it, it's resilient is not a thing that you do as an afterthought. It has to be there from the system design. And this is what we hope that we will motivate people to think about. So in addition to this, I mean, while working on something together, you could see a lot of passion in this work. Most of us worked for free. Dimitris worked for free. Manolis worked practically for free. Christian helped us for free. BSc had some money from the EuroEXA project, but really minor money that so what you could see in this work is a lot of passion, which is cool. And then when we deliver the document, we say, okay, what next? And as it what next, we say, hey, let's have a safe house. Let's have a hub in Europe that will, be a starting point for anything related to resilient HPC. And we made it. So here's the web page. These are the founding fathers. I'm very happy with the people to contribute to this. Thank you for believing in this. You see that ARM is there. This is very interesting. I'm sorry we do not have Rayleigh with us today. And what do we do apart from the document that we delivered is we organize events like this one. So maybe it's the first time you see this, but basically some things happened 2 years ago, then last year, then 6 months ago, Christian was kind enough to also invite us to his workshop. Then here we are today. And we will continue because it's good for us to meet from time to time, to have a dinner from time to time, and to discuss these things, to see, okay, how we as a community move forward. What do we want to achieve? I don't want to change the world. Publishing conferences is great. It's still good. But maybe we need to think also about something else. Maybe we can also think whether our work can indeed improve the resilience of the HPC systems made in Europe. And this is maybe not much to ask. This is maybe just a small shift that will start with the way that we think about the job that we should do. And finally, how can you help? So again, it is 7 p.m. in Europe, and if you're listening to this, it means that you have at least a small passion about HPC resilience. So if you have experience in this area, if you think that you have advice that could improve everything we did so far and that could help us move forward, please say so. We are very happy to hear advice from others. This is why Christian is here. This is why other US experts are part of this community, because they know much more than us. They can give us different view. If you want to do brainstorming, workshops, yes, be here. Be part of the community. And also, I mean, if you work in resilience, just keep working. Keep digging. It's a very difficult area. It is not the most sexy area to work in. You will not have logs. You will not have models. It will be difficult to publish. Nobody likes to talk about it. Nobody likes to say, yeah, you know what, our system fails from time to time. So I understand it's difficult. Keep working. Thanks for being part of this community. While you're digging, well, maybe we should do, you know, some blueprints together before we start digging the ground. And that's all from me for today. So my email, yes, Mare Nostrum is by far the most beautiful supercomputer in the world. If you're in Barcelona, you want to see it, send me an email. I will make it happen. I'm super proud of my Instagram account. I have only one follower, so please follow me because I feel pathetic. And this is the hashtag that I like to use. That's all.
Thank you, Petar. There is a question in the QA box. It seems that from a hardware perspective, only ARM is engaged in this initiative.
Yes.
So a comment on that and a follow-up on that. The reason for this, and if others like NVIDIA and Intel will eventually join in the near future. So why only ARM? And if you see a path for major chip manufacturers like NVIDIA and Intel to be engaged as well.
So I mean, I don't know whether NVIDIA, when they bought ARM, they implicitly got engaged into this initiative. So this is a stupid answer. But no, the thing is that it's very difficult to. We did talk with Intel, we did talk with Micron, and we did talk with Samsung Semiconductors Europe. And there is a big corporate. It is very important to respect corporate view on this topic. And they are typically not too happy to make anything public or be part of anything that is not well controlled with their communication channels. So this is something I fully agree. I lost the question. I fully agree that it is very important to have support from the companies. We do have, BSC has strong support from some of these companies, but none of this is public. So they are very shy to put anything in the public domain. I told you it's not a beautiful domain. I mean, telling that your products fail, well, maybe just better to be quiet. And I think that this is general approach in community.
Okay, Petar. Another question in the QA box. I totally agree that resilience has to be there for system design, but it seems it's being neglected. And likewise, Christian's talk said earlier that funding is hard to find. So do you think more motivation is required? More people need to be convinced of its importance? So what's your take about these aspects? Funding and motivation and getting people engaged. Really the same discussion, but perhaps yes, a further element here.
Yes, so this is maybe for the panel. I mean, I fully agree with the question, and I'm trying to do that. I'm really trying to do that, and it's not easy. And you know that. It's not easy, and everybody knows it's not easy. Right? So, and I think that the big game changer in Europe is the idea that we should build our own hardware targeting HPC. And I'm glad, and this is a new idea, right? This is what, a decade? I don't know. It's a new idea. So let's see what we can do there. But again, this is probably discussion about panel. But
okay,
sorry, and I have to add something. If you talk about funding and everything, step number one in this direction is, again, guys, we have to unite. We have to make a common front line here. And if we don't do that, we're just a random of barbarians that's from time to time shout, but nobody takes into account. If you want people to take into account, you have to make a front line. And this is what I'm trying to do. And And this is what you're trying to do. And this is why we are here today. Thanks.
Thank you, Petar. So this concludes the series of talks that we had scheduled for today. Now we have a panel with our speakers, and we will be taking questions from the audience. Petar, we were supposed to have a 5-minute break. I don't know. I would say we should not truncate the panel, so I would prefer to skip the break. If it's all right with the panelists. Okay. So okay, that's
Yes.
fine. I mean, we can get started. We still have a number of attendees, which is great. As Petar say, well, there has to be something for you here to be still with us. Okay, let's get started here. So as a structure there, I would suggest two things. I would like each of you to highlight a point that you personally think is, let's say, a pain point in the direction of resilience. Can be directly related to your talk, can be more broad reaching. And then I would like the others in the panel just to comment on that. So, for example, if Petar makes a comment, the other panelists make a follow-up on that. And we do in this way. We can do a round. Just try to keep it very short, so it's to the point and a bit sharp. It's okay to make a future forward-looking statements. It's not a legal environment, as far as I know, right? Petar, I don't know if you've made any arrangements for that. So we have, yeah. Anyway, so
I see Christian is laughing. I see Christian is see he knows, right?
He knows. So I'll try to follow the. If it's all right with you, I would like to start to go with the order of presentation. So Christian was the first speaker, so perhaps he should make his own statement and then accept questions from the other panelists. And I'll be monitoring the QA box, try to see if there is something that complements the discussion. So Christian, is it all right for you to get started? Yeah.
Sure.
That's fine.
So as I mentioned in my talk, basically we need to focus on resilience by design, and there needs to be a purpose behind it. We shouldn't be doing just resilience for the purpose of doing resilience. We need to basically have the motivators correct, looking at the real data that's coming off these systems, and also the motivation that comes from the vendors, right? So you do need to take a look at the process technology roadmap that's put out there every year. There's also the IEEE Rebooting Computing Initiative that is taking a look at reliability issues. Reliability is a long-term problem and we need to fix it by design. And there was this question about funding. Again, we need to find the right motivators, right? So maybe the right motivator may be to argue that we should develop smart systems that are able to fix resilience issues or reliability issues autonomously using smart technologies without having sort of this manual thing going on with checkpoint restart intervals, and checkpoint restart themselves is mostly manual these days. That's my short statement.
Thank you, Christian. So, Yves, would you like to respond to that, or you know,
well, I'm not sure.
Counter it if possible?
Say that again.
So what would be your comment here? And perhaps you don't need exactly to agree, for example, about the checkpointing part, optimal or not.
No, it's okay. I think what history tells us is that the future is very hard to predict. And if we look at the evolution of parallel processing, I mean, it took 30 years to come with a massive parallelism, and many, quote, experts were predicting that we would never assemble millions of processors. So you don't know anything about the future of platforms nor for resilience mechanisms. I just like to, I like to say that if we want to assess the performance of some approaches or mechanisms, we need to have models, and we need these models to be public so that everybody can check they're not biased. It always strikes me how, I mean, people can have definite advice on the future of some techniques in the resilience community, and I think we should be more modest and you know, put the models and the equations and let the future decide. And my second minor point is that I've been you know, wondering how to gain access to data, especially on the frequency and the locality of silent errors. And while there have been some benchmarks for failures, it seems there are none yet for silent errors, and this is really lacking for the community. I think that's it.
That's a great comment, the access to data. Dimitri, your response?
I would say, and I will link that to not only to what Christian said, but also to what Petar said at the end of his presentation. I think that we should try to motivate funding agencies and also people to get involved in resilience, proving that it is not an ugly topic to work on. Because I think it's the topic that makes our systems work. If resilient provisions were not there, I don't think that even a laptop or a mobile device would work as it works right now. I think we should find arguments to convince that it is not an ugly domain. That's my take. The extra point I would add is that it's definitely a holistic or a cross-layer approach that needs to be followed. It was obvious from the discussions in the presentations that we need information about node failure rates, CPUs, GPUs, DRAMs, etc., interconnects, the software implications on it, and every other piece that I think Christian in his long talk very nicely presented. I think that should be the main point. It's not an ugly, and it needs cross-layer or holistic approaches.
That's fine. So let's move forward. So Isaac, what is your take on this?
For me, continuing with what Yves said regarding the data, is what in my domain, and this is what I'm doing, is what I miss the most. Like if you're trying to find public data, it's not possible, and at least not for updated data, because as Yves said, it's quite old, the one you can find publicly. But even not publicly, because if you go to another data center, if you go to a supercomputer and ask for their data, you're not going to get it if you don't work there. Maybe even if you work there, it's difficult to get it. So maybe what's needed is somebody that stands up and says, okay, here is the data. Here are the results. I'll do that. I know that that's very complicated, and there is a lot of bureaucracy here, but I would really encourage any center that wants to publish their data to do it, and maybe we can all gain very fine knowledge from there.
So sorry, I have to jump in. I mean, sorry, Ploumidis, sorry, forgive me, but I have to jump in here. And I will tell you what I was doing for last 5 years at least. So I was going to all European centers, tier 0 centers, the biggest ones. And I was asking them, is there any way that we share our data on failures? Under the NDA, nothing to be published. We give you our data, you give us your data. So how many bilateral collaborations do I have? Tell me the number. Zero. Even under these conditions, right? So this is very, and BSc, and I have to say, BSc is pushing really hard for this. Internally, I got permission from our directors saying, yes, we can make this deal. If your center, for example, Christian, if your center shows your data, we can give you ours. No publications, high confidentiality, whatever, we can do this. But I mean, it's very difficult. It's very difficult. And you know what is sad? And I'm telling to all of you, these centers are paid by public money in Europe. And at the point they get the public money, they say, no, yeah, but this data is confidential, you know, tricky. Intel doesn't like it, or whatever. Or Bull doesn't like it, Atos doesn't like it. Because in French institutions, the logs don't belong to CA, they belong to Atos. Anyway, so it's very difficult problem, and but I think that if we don't push enough, we will never change it, right? And I think that US there is actually much better with all the initiatives that you had. That I think that we can follow and hopefully learn something for you. That's it. Sorry for interruption, but I wanted to say on this.
Yeah, it's a reasonable point. Mm-hmm. So, Manolis Ploumidis, your reaction?
Yeah, I'm most probably newer than the others on the topic of resilience, but the problems that I had was once more the data, and having read some studies, it's also, I don't know, even if you have the data, how is it to analyze them? So there are, for example, algorithms to remove duplicate events, to assign the proper severity level on events. So even if you have the data, maybe it's also a bit difficult to process them. And also in the literature, there are several models that describe failure intervals. They provide some statistics, even if you don't have access to the data, but there is some top level description, even a very rough one. And again, the problem that at least I had is that another limiting factor is that if you don't have access to a large cluster or a simulator that is able to handle large setups, you are not able to produce any results, which means that maybe if you are able to produce quite good results that would attract attention.
Okay, Manolis. So, Petar, any further reaction to Christian's talk?
I mean, of course.
Of course, I counted on you.
That's as some of you know, they don't allow me to talk at home, right? So this got out. So I mean, I would really like to thank to all the panelists and because we are learning. I mean, this workshop, I think it was a great technical content, and we are learning from each other, and I'm learning so much from you guys. And one of the good things that the community is so small is that we don't hate each other. You know, we see, at least as I see you, as brothers in arms, right? The enemy is, let's try to convince the community that what we do matters, not like, oh, let's backstab Dimitris so I publish one paper more, right? No, this is, so this is very nice. I mean, talking about the funding, and I will talk now about Europe, because Europe is not US. It's different ecosystem. And again, here the idea is precisely to give this European flavor. What's going on here, guys? I mean, I have very specific note for you. This year we have to work on ETP for HPC strategic research agenda. Are we going to make some noise there? A lot of noise, a lot of synchronized noise. I mean, Europe is investing, and this is, oh, I love politicians, you know, they're investing in manufacturing 4.0. Voila. I did not know that 3.0 is there. But anyway, 4.0 manufacturing, right? This means that the factory, what Christian said, you know, the factory, whatever, fails and then it fixes itself. So can we sell our supercomputers as this factory 4.0? Because we have to deliver a service, it fails, and it doesn't fix itself, right? You need a guru programmer to figure out what's going on there and to say, okay, let's do something. And most of the time you just say, it dies, get it out. So that's it. I mean, if action, ETP for HPC strategic research agenda is coming out this year. Let's think about this. We have time.
Thanks for this comment, Petar. So just for disclosure, so Petar and myself had some involvement with the ETP for HPC documents. For better or for worse, let's try to do it better this time, Petar. Okay. Yves, what would be your statement, a major point that you would like to pose to the panel?
Well, I'm not sure. I like to hear about these initiative at the European level. It's still not clear to me how you achieve that. There is a strong competition for the EU projects. So, you know, INRIA is working a lot with several partners, but there is nothing, I mean, the picture is not as nice as Petar would designing it. So,
right.
I'm sorry, I have nothing dramatic to say.
Okay, it's that is fine. That is fine. Just to follow on this, about the funding situation in Europe. So a major vehicle for funding at this point has been the European Processor Initiative project, and let's say activities that will follow out of that. They are under the purview of an organization called the EU HPC joint undertaking, which is running through its paces now and trying to set up calls. Now they prefer, let's say, few large proposals, which is an item that really discourages research heavy proposals. They prefer more closer to, let's say, products or early products. And I think this is a parameter that we have to keep in mind. In the QA, there is a question that I will read to the panel, and perhaps one of you can pick it up, or several of you can pick it up. A possible solution could be to put together tier 0 centers, hardware vendors, application developers and owners in a specific project. And the suggestion is what the Euro HPC calls centers of excellence. There is already a center of excellence for performance. I think this is coordinated by BSc actually, right? And why not go for such a funding proposal on the topic of resilience towards exascale? Have you already tried this step? I mean, Petar, I know we do not have such a proposal yet. No such call is available. I don't know about the other of the colleagues here, if they have a comment about that. So to follow up on what Yves said earlier, perhaps an initiative of such a focus might be hosted by Euro HPC, but there is no appropriate call at this time. Not something that we can say, well, this is on the topic of resilience per se, even acknowledging the resilience concerns as we see in current calls. It has never been a priority one focus. Not at the hardware level, not at the software level. And I think this is a problem that we have at this point. So it's something that we need to keep in mind.
So sorry, Manolis, I have to interrupt you, and you will.
Of course.
I think that the problem is not that resilience was not priority one. The problem is that resilience was not there at all. At all, zero. Or that people set a project and say, okay, let's put 6 person-months into checkpointing. And we say, I mean, resilience should not be priority one, but it cannot be disappear. It cannot disappear, right? So this is a question, right? And I will tell you, this is and that's it. I mean, I don't know. I don't want to be priority one, but let's leave some money for that. Because I mean, there is a beautiful statement from John Davis from BSc. He says, I mean, if you don't have resilience, I don't care what you're building, I'm not buying it, period. So if you want to bet on this commercialized of European technology, whatever, I mean, that's it. I mean, anyway, sorry, I got lost. About Center of Excellence, it was a message from Piero Lanucara. Let's all think about this. Let's all think about this, and maybe not Center of Excellence, but there will be call for proposals soon. Let's all read it and let's figure out how we do this, right? But before that, I think it's also we should influence strategic agendas and politicians, because finally politicians are the one who drive the money. Anyway, so that is sorry. This is my. I got excited. Sorry.
That's nice. We're trying to get you excited so that we have enough energy for this type of work. So just to fill in a detail, so far we have been trying with Petar and other colleagues to find, let's say, possibilities to fund this type of work in existing projects that have slightly different focus. So you will see a large list of projects that are associated with this particular event. Various colleagues were gracious enough to allow us to use the logos of these projects. In each of them, there is at least one task that is on the topic of resilience or in topics pretty much related to the research and activities that you presented here today in the panel. But it's never a, let's say, a tier one, let's use this term probably, activity. So yeah, that's the situation.
There was an
for better, for worse. Yeah,
there
pardon?
was an exception, if I can interrupt you, Manolis.
Of course, please, Dimitris.
Was the Clereco project, which is the one that I was involved in. This tool I presented was generated from this. Clereco was resilience only.
Okay.
I don't know if you had the chance to have a look at it. That was that finished 5 years ago. It was cross-layer resilience. So we integrated resilience from the transistor level, going through the microarchitecture, the architecture level, and up to the software layers. We had some interesting case studies, but the project was reliability, resilience only. And I believe it was the only project of that focus during FP7, Horizon, or the recent years. The parameters that we wanted to stress, and I think we did that sufficiently to some sufficient extent, is to correlate resilience with the other parameters. Resilience is an important parameter, but it is not standing alone. It is, as it was obvious in the discussions today, it is correlated to performance. It's a sibling of performance. It's a sibling of energy. It's a sibling of power, of whatever you want to analyze. It's also a sibling of security, if you want, because you can combine resilience and security considerations. Some people consider them, contradicting, that they have contradicting requirements, resilience or security, depending on how you want to see the system. You want it to be more open to detect the faults, the errors, or you want it to be more close to avoid intrusions. So there are other parameters that should be combined. I agree with you, Petar, Manolis, that resilience at whatever level, but certainly for HPC, should be top tier priority, but not alone and not emphasizing its standalone nature. It is a combination of all the other parameters, because whatever decision you make in one of the parameters, it affects the others.
Okay, that's a quite sensible point, Dimitri. Let's see. So would you like also to make your, let's say, statement at this point?
That would be my statement.
That would be like perhaps to expand a bit.
A little additional one, which I don't know, maybe I think that Christian would probably have some answer or some comment on that. The availability of information from the vendors, from the processor vendors. That was one of the questions that I sent you, Manolis, and you asked Christian during his talk. I think that the question is how much information you get from the vendors, Christian, CPUs and GPU vendors. Do they provide you with any model or any additional tool that you can measure something before you start deploying your system? And the second comment from my side is that Europe will be really strengthening itself when the EPI processor starts materializing, and really, it should be the starting point for the European HPC and other computing domains. I think that not relying on Intel, on AMD, on companies would be a good starting point for Europe. So Christian, I don't know if you want to comment on the first point and the second.
I mean, I can comment a little bit. As I mentioned already during my talk, we do get some information that's under non-disclosure agreements, but not necessarily everything, right? So especially the processor and GPU manufacturers, that's where they make their money, right? Also the memory vendors, right? They're certainly not going to give up a lot of data. In fact, a few years ago, we actually worked with one of the manufacturers in trying to do a reliability analysis on a piece of hardware. And we required the manufacturer's insight to understand what was going on with that particular piece of hardware. And we discovered a new failure mode that the original manufacturer did not know. And the problem was, since we worked with the manufacturer and the work was under non-disclosure agreements, we did not get the lawyers from the manufacturer to sign off on the paper. So this work has never been published and will likely never be published, despite the fact that we worked on it. This is some of the problems we basically face, but it's something that will not go away. You will not get any sort of numbers from NVIDIA about their architectural vulnerability factors for different parts of their GPU. This is all inside information that they will keep as closely held secrets. What you will know is that they're working on these kinds of problems. They are well aware that problems exist. The same thing with memory vendors, right? So memory vendors, they basically work every generation their magic and changing the memory layouts so that you do get less double bit errors and stuff like that, right? But in the end, they do other things that are just secret sauce, you know, that are you won't ever hear about, and you certainly won't get the data, right? So and interestingly, when we started operating our Summit system, I did get a call from a memory vendor who was asking me about the memory error data, because we have HBM2 and the high bandwidth memory 2 in there. And this memory vendor was a competitor. And he basically wanted to get our memory error data. I had to explain to him that, you know, it's a little bit early for that because the system hasn't operated yet for, you know, only a few months. So getting any serious memory error data, maybe now after what, something like 2 years of operation, we can start looking at memory error data. But even so this is even how competitors try to get each other's data, right? So I don't see, we need to learn to live with the fact that we don't have access to all the data. As a research lab, what we started doing is we hope that we can publish more of our data that we actually own. With the supercomputing paper I was referencing to, that about the GPU failures, the failure data is public. We put the failure data as well as also the scripts, how we analyze the failure data on GitHub. And this is part of the paper. There's a DOI for it. You can access all the data you want and play around with it. But this is the particular only the GPU data. It does not include the allocation data or how, meaning which application ran when. It doesn't include which application ran where. So you won't see that, right? So, and to another point that was discussed earlier, giving out data, center data, one of the problems the centers are afraid of is that people basically take the data and make them look bad, right? And you have to establish a certain level of trust. And the only way to do this is to work with experts at the center in analyzing the data, because oftentimes people misunderstand what the data even means. Because not every event that's getting logged as a failure is an actual failure. Because remember, when a failure happens, an application fails, you get actually maybe hundreds of thousands of failure events getting logged, but it's only one failure that you actually experience. Everything else is just cascades, right? So, and these kinds of understanding, or this kind of understanding is required, right? So there was a question, I think, regarding anonymizing data or something, right? Yeah. Wow.
Yes, the question was, so could data be used only anonymously? I assume after some anonymization phase. Is this a possibility?
I think this has been already a little bit researched. It's problematic because ironically the same, well, let's put it this way. We worked we had a similar issue with that. We worked with a vendor on certain publications, and the vendor pulled out of the research. They basically said they cannot pursue this anymore because they have discovered a paper that re-engineered some of the hardware features. So this was basically data that this vendor put out publicly. And then a university student actually looked at the data, analyzed the data, and re-engineered which resilience features this particular hardware vendor actually employs. So that's something that the vendors are, and the data was anonymized, right? So, but it's still, you can still identify what type of technology is used inside these chips when you analyze the data, right? So that was one of the problems, right? So that even with anonymization, you can figure out, reverse engineer certain things. And that's what they're mostly afraid of.
And we have a proof here on the screen. Check Isaac. I mean, I give him 2 liters of coffee. He will break any anonymization that you do, right? So, and sorry, I will just to back up. I mean, everything Christian said. I mean, it's scary how much we agree. Maybe because I mean we're doing the same thing as a system provider. But everything you said applies to us. And even this thing, like you publish the data, somebody will make it look bad. And then the best thing is publish nothing. And it's really, I would like to thank you for your supercomputing paper on GPUs, where you also, I mean, only publishing absolute numbers that you did is brilliant. Because typically what we see is relative numbers over relative numbers over relative numbers. So you really don't know whether the problem exists, right? But I mean, even publishing absolute numbers is tricky, and you did it, and it helped me to convince some of my bosses that the problem exists. Because I mean, when you have a paper that says out of 18K GPUs, we had to replace 11K. I mean, I sent this quote to one of my bosses who told me the problem doesn't exist. I sent him and I said, I will find the guy who had to replace those GPUs, and I will tell him where you live, you know. so anyway, so that's it. Thanks, Christian. Thanks for everything you did for us. Thanks for advices that you're giving us. And that's all. And beware of Isaac. Beware of Isaac. He's hacker. Look at him. He's hacker. Put your hood, Isaac.
Now that Isaac is in a good mood, so Isaac, what would be your statement? What would be your, pain point, or most promising direction that you would like to pose here in the panel?
Maybe related somehow to anonymity, but taking it to my domain, that's more machine learning. Maybe we don't really need to share anonymized data, but maybe there could be a way to train the models in different computers without sharing any data, but somehow join them. Making a model, a predictive model, for example, that is trained with all the data independently, where it's very difficult, if not really impossible, to extract information from the different people who trained it. So maybe there is a kind of middle point to meet here, and it could be an opportunity if different centers would like to collaborate on something similar. And it's probably something to explore.
Oh, that's quite an interesting point, Isaac. So reactions to that?
I have to add, sorry, and then I will be quiet. I will be on mute until the end, I promise. business is made by gentlemen's agreements. Going public, all the way public, is maybe too much in the first round. But making nice agreements, bilateral, and making or with a small group of people, for example, people working in resilience in Europe or Christian, or is maybe a good place to start. And I'm now officially or opening this option for people at the panel and also people as the attendees. Maybe we can start small and then make a critical mass and then convince the rest of the community. But BSc is really open. BSc is the only center in Europe that published something, some logs, not logs, data, absolute numbers. We are pushing for this, and we have this culture. Or let's do something together, and let's do something at least point to point, and let's grow together. So that's it, and I'm done for today. I promise. I'm on mute and.
Okay, so it's this question of trust again that comes up in this type of collaborations or establishing the foundations of collaboration. Let's see how it can turn out. So Manoli, you have a statement or pain point or direction that you would like to highlight at this point?
Just simply the things that are missing, at least for the things for part of our work is, and I don't know if also in some papers I have read that they tend to failure blocks are also related and affected by the type of of applications and the load that is on the cluster. I don't know how is it to capture them, how can you release these things. And also, again, major problems, access to big systems or how to or simulate or a big simulator, for example, to replay all these things.
Okay. Follow-up comments on this from the panel? Do we have a simulator that can support a large number of nodes? Christian, I know that you have worked with Xing towards this direction. So
yeah, I mean, yeah, sure, we can develop simulators, all kinds of simulators actually, to do this kind of work, sure. So I wanted to pick up on something that was said earlier. So I know as actually Yves worked in that direction too. The idea is to use synthetic data, right? So you're basically, instead of taking real data, you're generating synthetic data based on assumptions. And you can generate different synthetic data based on different assumptions. And that allows you to do experimental studies without actually even ever knowing what the real data looks like. And you can still do trade-off studies. You still can do lots of other kinds of interesting studies, and then basically tell the centers, hey, just take a look at the synthetic data we use and how does our synthetic data match to your real data, right? So this is basically the whole idea of having digital twins, where you develop actually a digital twin of a real system, and the digital twin basically generates synthetic data, right? So, and you're basically just trying to develop different digital twins of different types of systems that have different resilience or reliability properties, right? So this is certainly a way forward. And this can be also then used in terms of simulation and also large-scale simulation.
Thanks for this comment about synthetic data. So if you allow me to make an extrapolation of that. So for the performance evaluation, we have all sorts of suites of benchmarks. We have SPEC, we have TPC, and many variants of these. Any chance of, I don't know, providing a standard set of tools for evaluating resilience, benchmarking, let's say, a system from the point of view of fault handling and fault behavior? Is it too far a stretch? Probably. this idea of getting a technique and tools to support the technique to generate synthetic data that match various assumptions perhaps would be part of such an approach. But how far are we from that? Is it realistic at all?
So when it comes to the big systems, they all get benchmarked based on performance, right? And performance means also resilience, because when we benchmark our new systems that come in, I mean, I'm not talking about LINPACK. I'm actually talking about the actual application benchmarks that we run before we accept the machine. And when we accept the machine, then we actually send out the check. And when the system is not reliable enough, then it doesn't deliver the performance. So it is sort of built in as a performance benchmark, right? And the same thing is for correctness as well. We check the correctness, our results as well, and they need to be within a certain error margins. And when we look at the big systems we acquire within the US Department of Energy, we basically have these huge application acceptance suites where we have lots of different applications that these systems need to run, and they need to run them at a certain performance benchmark and at a certain correctness, right? So in practice, there is something like that. It's just not called a resilience benchmark, right? So, and in terms of using then artificial data or models to basically, I don't know, I think we're still far away from that.
Okay.
Sure. If I may add the word, I concur. There is some data, but not enough. For instance, if you look for characteristic of applications, when we were working with colleagues in Sandia, we use the Apex workflow, and they give a lot of things like the duration of the jobs and the checkpoint time and the I/O volume, but you don't know, for instance, how the I/O is split into either burst, very short burst, very intense, or if it is scattered throughout the execution. There are indeed a lot of missing information. So it's not only traces from failure logs, but benchmarks from application characteristics that are missing. So I think our community has a long way to go before we can, gather the relevant information. And just to say a word also on synthetic data versus traces. Of course, synthetic data, they allow you for a more comprehensive study, and you can explore a wider spectrum of parameters. But actual traces, they point to your relevance, because there are many people who want to see how relevant, how practical your scenario is, and they are to be convinced only with traces. I mean, you can use as much synthetic data you can think of, that will not be enough. And finally, I'm sorry, I just want to say I enjoyed this lively discussion, but I have another important meeting in 2 minutes.
Okay, sorry for taking, for overrunning.
It was very nice discussing with everybody. It was very lively. So thank you again, and I hope to discuss with you all in the near future. Thank you.
Thank you so much for taking the time to join us. Take care.
Bye-bye.
Thank you, Yves. Thanks.
So I guess we can probably wrap up. We are now beyond the graceful 15-minute late, let's say, interval. I'm very grateful for all of you to be available and lively and let's say willing to express opinions, etc. And I hope we have a chance to create a similar event, hopefully a physical event this time, not just via the conferencing facility. And I think that we all learned something today. If this is the case, then it was a successful event. I hope that we have a chance to keep up, and what Petar said about let's say continuous effort, community building, etc. I think this applies to a great extent, and I'm really grateful for your participation and effort. Petar, any closing words from your side?
Just a big thanks to to everybody, to people who panelists, to people who are still online, or maybe that it's a bot, right? I mean, we have 20 bots.
I think these
you.
are.
It is very difficult road, and it's good to see that we are not alone. So
Yeah.
and thank you. It's a very nice community to be part of. Thank you all, really.
Thank you.
Thank you for organizing this, guys. Thank you.
Okay, let's look forward to better opportunities. Again, very much obliged for your time and participation. I will be asking for your presentation material for filling up the website in the coming days. So we'll expect this request. And well, take care. Many thanks to the audience. We had, by the way, quite a high number of registered attendees. We were in the top 3 or 4 events of the conference. I mean, from the sessions, which is quite good. And I'm pretty sure we can do better. So take care. Thank you again for your time. Bye.
Bye-bye.
Bye.
Thank you. Bye-bye.
Bye.
Bye. Thank you.